Pak Vicky, apakah sudah bisa dimulai?
Oke, Bu Dini, silakan. Okay, we can continue. Thank you for the chair.
Thank you very much. Good morning, everybody, all distinguished participants. I welcome you to this second parallel session in Biocomposite. We will start this session with our invited speaker. We have two invited speakers. One is Dr. Henry Fahabi from University of Florence, France, and the second speaker is Dr. Ariadne Yuwono from University of Indonesia. It seems both of them could not attend this session. So for now, we will just watch their video. First, I would like to read their short bio first. Dr. Vicky, can you help me to display the short bio of Dr. Henry Fahabi first, please? Our invited speaker is Dr. Henry Fahabi, received his PhD in material science from University of Montpellier, France in 2011. Since then, he joined the University of Florence, France as associate professor. Can you please go back, Dr. Vicky? It seems the short bio is moving by itself. Maybe we can just use by slide. No need to play the slide. Yeah, this is fine. All right. Dr. Henry Fahabi main research interests include flame retardancy of polymeric materials and nanocomposite. He has authored over 130 peer-reviewed scientific articles, book and book chapters. He is now a committee member of the Fire Group of the Chemical Society of France. Since he is unable to attend this seminar directly because France is now 6 hours behind us, so it's quite early or maybe too late there. So we are going.
Recording in progress. Recording in progress.
Well, here you have an interesting slide about the time needed for escaping from a building in fire in 70s and in 2015. So you can observe the time decrease from 17 to but how we can explain the reaction to fire? It can be summarized by the acronym first, several parameters, flame spread, ignitionability, rate of heat release, smoke, and toxicity. All these parameters are important, but the most important is rate of heat release. You have a typical curve of propagation of fire or development of fire, temperature as a function of time. During the first step, temperature increases and we arrive to a very crucial step. So this step, the flashover, is a really crucial step in fire propagation, and we try by using the flame retardants to avoid this step. You know, of course, this famous fire triangle with three elements: heat, oxygen, and combustible. In fires, generally, the source of heat is accidentally, like an electrical problem, a cigarette. You cannot avoid it. You cannot put your house under vacuum. So finally, we can only play on polymers by adding additives, flame retardants. In the case of polymers, we use these additives and to suppress one element and so we try to increase the time of ignition and the and it's not a new history. In the past, Roman but finally, the science of flame retardancy began in 19th century. At that time in Paris, we had several theaters, and the presence of candle and cotton-based cartons led to fire. From that time to now, we had a lot of evolution in flame retardant solutions, and you have here some of these solutions today. Of course, these solutions are evolved in function of the evolution of processing, and for example, new processes but how we can add the flame retardants to polymer, generally we have three methods, three ways. By melt blending, for example, in extrusion, by chemical modification and putting the flame retardant element on. Of course, it's possible to measure the flame retardancy at several scales. Of course, the best one is a real scale, but it costs. So we have the micro scale test. Some photos of these tests. There are several types of flame retardants nowadays, and in function of type of polymer and processing, you can use them, like halogenated flame and you can find these flame retardants everywhere. But for answering to this question, why using the bio-based flame retardants, there are several points. Some of these halogenated flame retardants, efficient halogenated flame retardants, are banned, and some other ones are on the list and will be banned soon. At the same time, the fire regulations are changed and they are more and more drastic, and we need better flame retardancy level. Also, we should consider the sustainability issues, and retardancy. Here you have a scheme extracted from our review paper showing different bio-based materials used to synthesize new flame retardants. We can how a flame retardant works in a given polymer. There are mainly two modes of action in gas or condensed phases. I don't give you the details here, but for the bio-based materials, generally we don't have the action in gas phase, and the action happens only in condensed phase. I mean in bulk material, by creation of char residue, because these bio-based or biomass materials are generally a source of carbon, and this charring acts as a barrier or shielding effect during the combustion, and in this manner we can improve the flame retardancy of polymers and our material. Here you have the scheme of creating the char residue during the combustion on the surface of polymer as a barrier during the combustion. So I will give you here three examples. So the first example is the use of tannin, which is a biomass material and is a source of carbon. We combine the tannic acid with phytic acid, which is a and here you have the chemistry of the final obtained flame retardant. We incorporated this flame retardant into PLA, a bio-based polymer. Here you have the curve of heat release rate obtained in concalorimeter. Heat release
satu dari 17 tujuan global yang tersusun dalam Agenda Pembangunan Berkelanjutan 2030. Pembangunan berkelanjutan atau Sustainable Development Goals berusaha melindungi, merestorasi, dan meningkatkan pemanfaatan berkelanjutan ekosistem daratan, mengelola hutan secara lestari, menghentikan penggurunan, memulihkan degradasi lahan, serta menghentikan kehilangan keanekaragaman hayati. Biodiversitas Indonesia menjadi aset jangka panjang yang perlu terus dipelajari, dikaji, dan diteliti untuk kesejahteraan bangsa. Badan Riset dan Inovasi Nasional atau BRIN tidak hanya memiliki para periset unggul, tetapi juga fasilitas-fasilitas riset dan berbagai aktivitas riset untuk menghasilkan riset yang bermanfaat bagi rakyat Indonesia. BRIN memiliki berbagai laboratorium, seperti Laboratorium Analitik dan Mutu, Laboratorium Biosafety, Ruang Bersih, Laboratorium Klinis dan Medis, Laboratorium Inkubator, Laboratorium Produksi, dan Laboratorium Penelitian dan Pengembangan yang tersebar di beberapa daerah. BRIN juga memiliki laboratorium alam, di mana setiap lokasinya memiliki karakternya masing-masing. BRIN mengelola 5 kebun raya dan membina lebih dari 37 kebun raya daerah yang dikelola pemerintah daerah dan 3 kebun raya daerah yang dikelola perguruan tinggi yang tersebar di 23 provinsi.
Once we
Recording in progress.
from him, we may also suggest you all to email him personally. Okay, now the second presenter is from Dr. Ariadne Yuwono from University of Indonesia. First, I would like to read her short bio. Please, Dr. Vicky, can you help me to play the short bio? Dr. Ariadne L. Yuwono, M. Engineering, PhD, received her PhD in Material Engineering from Monash University, Australia. For her achievement and contribution in physics, Dr. Yuwono has been awarded with several prizes, including the Best Researcher in Sciences from University of Indonesia in 1997. In 1989, she joined the Department of Physics at Universitas of Indonesia as a lecturer while conducting research on the development of nanocomposite, composite, and material science for several applications. She has been one of the judges of the L'Oreal for Women in Science Award, sponsored by UNESCO, KNIU, and L'Oreal Science in 2008 until now, as well as in the Young Researcher Contest organized by LIPI in 2011. Her current research interests focus on nanocomposite, composite, and green composite for structural application, modification, and characterization of clay for catalysts. The research activities include optimization of biodiesel productions using pillar bentonite as catalyst, development of natural fiber reinforced composite for structural application, and composite for earthquake and fire-resistant buildings using sandwich composite structure for disaster risk reduction. She has authored and co-authored more than 50 scientific papers and granted 4 intellectual property rights documents. Thank you, Dr. Vicky. Can you please play Dr. Ariadne video, please?
Good morning, everyone. I'm Ariadne Yuwono from Department of Physics, Faculty of Mathematics and Natural Sciences, Universitas Indonesia. First of all, I would like to thank the ICONLIG 2022 webinar committee for giving me opportunity to present my research results. The title presentation today is Bamboo Fiber Reinforced Polymer Composites, Properties and Applications. The background of our research was that we studied that green composites have been developed by researchers and industry for the last 2 decades. And the using of synthetic fiber as reinforcement in the composites causes some problem. One is the environmental pollution. The second one is potential health hazard. And of course, the third one is depletion petroleum reserve. So that we choose bamboo fiber as the reinforcement for our composites. And we also studied that the bamboo fiber applications are textile industries, paper making industries, constructions, composite materials, in composite material industries, including aerospace, marine, automobile, furniture, and sport. In Indonesia, the application of bamboo fiber, most of the application are not in structural application. However, in 2017, 2 researchers started to research about composite boards. And 2019 is about motor footstep, cars ashtray, and 2020 cars bumpers. So why bamboo fibers? Bamboo fibers have a number of benefits. The tensile strengths of bamboo fiber are relatively high, about 140 and up to 800 megapascal. The modulus of elasticity is about 33 gigapascal, and this number depends on the sources of the bamboo fiber. This tensile strength and modulus elasticity are high because the cellulose content in bamboo fibers also relatively high, and this providing good mechanical properties. And high mechanical properties is one requirement for material structural application. Another benefit is the price of bamboo fibers are relatively low. It's about $1 per kilogram. The density of bamboo fibers is between 0.6 up to 1.5 gram per centimeter cube. Once again, it depends on the sources of the bamboo fibers. And the plant life cycles are relatively short. After 3-4 years, we can harvest the bamboo fibers. In Indonesia, there are about 120 species bamboo fibers. However, there are also challenges on using bamboo fiber as composite reinforcements. From this picture, we can see that the cellulose content is quite high. This is one requirement for good mechanical properties. But the lignin content and the hemicellulose contents are also quite high. So the challenge is how to remove the hemicellulose and lignin. So the extraction process is very important, so that we design the extraction of bamboo fiber for composite reinforcements. So the research objective of this current research were to optimize bamboo fiber pretreatment parameters and characterize them, to produce bamboo fiber reinforced composites that comply with the SNI 03-2105/2006. This is for particle board standard, and to produce automotive product that met the market standard. So we created experimental design that were divided into 3 stages. The first stage is bamboo fiber pretreatment. We use 3 different bamboo fibers. They are identified as SBT, SBH, and SBG. So the pretreatment of bamboo fiber were alkalization and alkalization plus steam explosion. We varied the time or the duration and temperature and and as well as the content of the sodium chloride. And the characterization is density of the RR and single fiber test. And we analyze the result, and we have the pre-treatment process parameter and the SBT and and then the SBT and HBS are the outcome of the first stage. Second stage, it was the composite fabrication. From the first stage, we used the SBT and SBS bamboo fibers. We did the same thing, alkalization and steam explosion. This is the best fiber pretreatment. And we also did the particle processing into different particle sizes. So that on the composite fabrication, we varied the volume fractions and the particle sizes. And we use also thermosets and thermoplastic polymer. The thermoset is polyester, and the thermoplastic was polypropylene. We characterized them. We did the mechanical tests that they were tensile and bending stress, and also we did the morphology. The analysis for this step, we obtained 4 different type of composite, and we get the outcome is, or the output is, the fabricant process parameters and polypropylene SBT composite. Then the third stage is the fabrication of composite board and motor engine cover prototype. Once again, we did the alkalization and steam explosion, and also particle processing, and we fabricate the PP SBT composite as particle board and engine and motor engine cover. And we do also the mechanical properties and physical properties, and the output was PP SBT composite boards and PP SBT composite for motor engine cover prototype. First of all, I draw your attention to the density measurement result. The density of the current bamboo fiber, the adhesive ones, was between 1.27 up to 1.24 to 1.27 gram per centimeter cube. And after pretreatment, the density increased up to 13% in this value, and this is also acceptable based on previous result. The bamboo fiber density could increase up to 24%, and it depends on the pretreatment process. The increases of density of natural fiber after acquisition are reported by these 2 researchers, and it says that the alpha cellulose was formed to create thicker cellulose cell walls, or it's called densification. And densification determines the increase of fiber density. We see the result, then the result is acceptable among other previous result. Now, the next slide is the single fiber test result. We from this result we get the average tensile strength. So we can see that we varied the duration of the alkalization and the concentration of natrium oxide, not hydroxide, and the temperature, plus this one is the steam explosion process. So by combining the alkalization and steam explosion process, we obtain the high tensile strength for these 3 different type of bamboo. The highest one is this. This is the optimum condition for SBT, and the second one is this. This is for the optimum condition for the SBH, and the third one is for SBG. So we can see that the SBT and SBH had the high tensile strength from this result. So that we decided to use SBT and SBH for the next step. So from the morphology, we we can see here that after the pretreatment, the fiber surface is rougher and cleaner than the pristine fiber. So this is the left after the pretreatment. Because the lignin content was reduced and increased cellulose content, then we can see that the surface is rougher, and rough surface provided a higher matrix and fiber interface bond. This result was published in Key Engineering Material 2020. And from previous studies, it is said that surface roughness become clear with the presence of more groove and more flakes and pores on the cellulose microfibril aggregates. This is result by three different researchers, and we can see that these are the LCM images for the pretreated bamboo fiber. Now we move to the second stage. We use the two different bamboo fiber, SBT and HBH, for making fabrication of polyester composite. For this step, the bamboo particle was mixed with polyester resin, and we use hand layup process followed by vacuum process, and we obtain the bamboo particle reinforced polyester composites. While for the composite fabrication for the polypropylene, with the same thing, we mix the SBT and the SBH into different type, of course, with the polypropylene pellet using an extruder, and we get the PP and bamboo particle pellet. And this pellet was injected into injection molding used in the composite fabrication, and we obtain the composite board. This is the propylene composite board. So the next steps that we did mechanical testing, that included the textural test and tensile test. For the polyester composite, the flexural strength, the highest flexural strength is obtained by the HBH polyester, which is about 50 megapascal. And for the polypropylene composite, the SBT, reinforced polypropylene composite, even higher, about 90 megapascal. And the next result was the tensile strength of the polyester, which is 27. This is also SBH polyester. And for the polypropylene, was 31 megapascal. So that we can see that the PP SBT provided the highest structural and tensile strength. We also observed the morphology of PPS for all composite, but for this presentation, I show you one set result of PP-SBT composite surface morphology by scanning electron microscope observation. On the first row, there are 50 mesh of particle size with three different volume fraction, fiber volume fraction, 10%, 20%, and 30%. The second row, 100 mesh with 10%, 20%, and 30% volume fraction, and the bottom row is the 250 mesh. And we can see from all this picture that the bamboo, the SBT or the bamboo particle well embedded into the matrix, and we don't see any voids in this product, so that we believe that there is a very good matrix and particle interface bonding. So that from the mechanical testing, and we can tell that the increase of particle sizes, which is 50, 100, and 250 mesh, and bamboo particle fiber volume fraction 10, 20, 30% were proportional to the flexural strength of the composite, or the 4 types of composite. And however, all the flexural strength of a composite were higher than the standard flexural strength of SNI, which is 24.5 megapascal. And for the previous result, we decided that the tensile strength and flexural strength of SBT bamboo fiber was the highest, so that we choose SBT bamboo fiber reinforced PP composite to be the used for the motor engine cover fabrication. In this case, we used 200 mesh particle size and 30% volume fraction of particle were applied. So this result was already published in Polymer 2020. So that the SBT bamboo particle reinforced polypropylene composite was fabricated using injection molding technique for motor engine cover fabrication. So on the bottom, this is our product, the SBT PP composite, and on the top, the blue picture is the polypropylene motor engine cover that exists in the market, and this also have these polypropylene materials have been used for cover for engine cover in motorbikes. So that at this moment we are in under registration process to obtain a patent. And the last step was we do also some mechanical testing to confirm the result of both the composite board and the motor engine cover. The first row is the SBT PP composite motor engine cover. We can see that, and the second row is the commercial PP. So we compare row number 1 and row number 2. We can see that the density of these two materials are similar, while the flexural strength of for motor engine cover is higher than the commercial PP, as well as the modulus elasticity and the impact strength. Well, row number 3 is the composite board, SBT PP composite, as also is the similar density, and this density is in the range of the composite board standard, and the rest of the value are in the range of the composite standard. So that in summary, both SBT bamboo particle reinforced polyester and polypropylene composite met composite board standard. The flexural strength of this material was about 91 megapascal, and the tensile strength was 31 megapascal with 30% of particle and 250 mesh particle size. And the particles were entirely embedded and covered by the matrix so that the composite had good homogeneity and minimum porosity. Motor engine cover prototypes were fabricated from SBT bamboo particle reinforced polypropylene composite and met the SNI standard. And the flexural strength was 94 megapascal, the modulus elasticity about 0.9 gigapascal, and this prototype, these values were higher than the existing commercial PP motor engine cover. This indicates that the 30% volume fraction of bamboo fiber particle replaced the polymer, so that this composite is an alternative material for motor engine cover. Thank you for attention and good afternoon.
Thank you very much, everybody. We are very fortunate that Dr. Yuwono, Ibu Ariadne, is actually now joined our session. So welcome, Ibu. Please allow me, my name is Dini. I'm a chair of this session, and we already play your video. So now, if you are okay, we will have into a discussion session. So now I would like to invite everybody. You can raise your hand by the menu. You can raise your hand, or you can just directly also ask question to Dr. Yuwono. Please, participant, anyone would like to ask Dr. Ariadne? Okay, maybe I can start, Dr. Ariadne. This is a very interesting talk. I see that you already make some product and it's already patented. My question is, since it's from bamboo composite, what do you think about the sustainability of this material? And then so we can make them into a product, and then we can also market them, make them like in a mass production, for example, like that. Can you please explain that?
Okay, thank you, Budini. Hello, everyone. I'll try to answer Budini questions. But sorry, this is calling for a praying.
Oh, okay. Sorry.
Can we just stop
Yes.
for
Yes, I
a
think we
minute
can
or
stop
so?
for a minute. Yes. Thank you. I didn't hear it here. Sorry.
Okay. Could you please repeat your question, Budini?
Yeah, Ibu. Bamboo is an interesting raw material for this. My question is, how big the potential for this product to be developed, especially in a mass production? Remember that is from the biomass, yeah, not from something that we can access easily. Thank you.
Yeah. Okay. As I said in the presentation, that there are about 120 species bamboo plants in Indonesia. So that in fact that the usage of bamboo plants in Indonesia still very low, and that then the bamboos have been used for non-structural application. So the availability is still very high. Of course, we should maintain the bamboo plants. However, you know, there are a lot of them everywhere. That is one thing. So that we are very fortunate that we do have plants everywhere in Indonesia, and the plant life cycle is only up to 4 years. So that to obtain to harvest the bamboo fibers, that does not take very long time, such as wood plantation. That is one thing. And the expectation is 30% replacement for polymer, also reduce the polymer content in the product. So we just hope that 30% means something, even it's very small. So that in the future, we hope that this product can be produced in a big mass. Yeah. And if you said that how it's you mentioned about patent as well, that before that we are already under process, and I don't know if we learn about TKT, I don't know if they are all Indonesian or they are other from Indonesian in this room, but TKT tingkat kesiapan teknologi, we are in level 4, so we still have to test in a real environment to be TKT 5, and still a long way to go to mass production. Thank you.
Okay, thank you very much, Dr. Ariadne. So the readiness level is still in the lab scale, yeah. But the patent itself is already promising. So we do hope the best for your product and for the development. We have now 2 participants. Yes, I would like to invite Dr. Yayan Nurhamia to ask the question, please.
Hello, Bu Adna. How are you? Hello, Bu. It's such a great pleasure to meet you again. After maybe like 7 years, I think, after I graduated. So thank you for joining us today. Well, actually, I did join when you presented your presentation, but I would like to ask, maybe not related to bamboo. So, do you actually work on polymer now, or do you focus on the natural fiber composite?
I didn't get all the words, Yayan.
Okay. Do you still working on polymer?
Yeah, still.
Yeah. What kind of polymer do you still working on now?
Okay. For the last 5 years, I've been working on green composites and using bamboo fiber, kanal fiber, pineapple leaf fiber. Yeah, 3 of them, and all of them now you see the product were composite boards.
Okay. So what kind of polymer do you use?
This is bamboo fiber, of course, polypropylene and polyester, and then and then epoxy and also polyester for the kanal fiber. I think thermosets and thermoplastics for different type of application. Yeah.
Okay. It's interesting. But thank you for joining us.
Thank you. Yeah.
I will message you again privately.
Thank you, Dr. Yayan, for the question. Now there's another raised hand from Mr. Denny Purnomo. Please, you can ask directly to Dr. Yuwono.
Okay, thank you, Dr. Denny. Good afternoon, Dr. Ariadne.
Good afternoon, Pak Denny.
Pleasure. It's very nice presentation is all about the bamboo as a reinforcement for the cover of engine. So my question is, how about the thermal conductivity and the thermal resistance that are for heat, the transfer heat? Just like that, my question. Thank you very much.
Yes. So the thermal heat is part of the next test, which is to meet the standard of TKT 5. So that, however, from the polypropylene, the commercial polypropylene already have been used for years in motorbikes, and reducing 30% using bamboo fiber, we thought that it didn't affect so much. But however, we still have to do the test, and also we also have to do some other tests as well to meet the the other standard for motor engine cover. Yeah, should answer your question?
Okay, thank you very much.
Thank you.
Thank you, Pak Denny Purnomo. Is there anyone else would like to ask directly to Dr. Ariadne? Any raised hand?
Ibu Lili.
Ibu Lili. Okay, please, Ibu Lili.
Okay, thank you, Bu Ariana. Thank you so much for your presentation. It was really great to hear your information about bamboo. It reminds me in the last conference in Bali that there is a big dome from bamboo, and yeah, it's quite interesting. My question is, do you have a particular concern on the type or the species of bamboo that you use for the reinforcement? Because we know in Indonesia we have a lot of species of bamboo, which is some is very tiny bamboo and some is very big, which is in regards to the harvest process and then the process from the beginning until it becomes the reinforcement for your product. Just curious what type of bamboo and is it like affecting your product? Thank you.
Yes, as we know that all the material from the natural product depends on especially natural products, especially plants, depends on where the plants were harvested, right? That's true. And the three types that we use, SBT, SBH, and SBT, SBH, and SBH, were harvested from West Java. And the bamboo was harvested after 3 years. So that is important. When or how old the bamboo itself, right? That is one thing, and where we get it from West Java, and then the second one is we use only the middle part of the bamboo fiber, not the bottom and not at the end. So that's also important. And all of this were explained in the previous publication, actually. Yeah. However, if we want to use other type of bamboo that harvested from different places in Indonesia, I think that we should do the same procedures for alkalization and steam explosion, and we have to see basically the tensile, single test fiber test result, the tensile strength of one fiber, right? So that is, I think that's very important. However, from our studies, previous studies, the values that we obtain are in the range of previous study result. So that the result, okay, there is, for example, the tensile strength could be from 80 up to 500 something megapascal. However, that's true, but specifically for this research, if we want to use different type of bamboo fiber, at least we have to do the single fiber test to obtain the tensile strength. I think that's important. Yeah.
Okay. Thank you so much, Bu Anna.
Thank you for your question.
Thank you, Miss Lily, who will become doctor soon, yeah, inshallah.
Congratulations.
Okay, is there anyone else before we actually close up this session? It's almost 12 o'clock. Yeah. All right, everybody. I think let's give a round of applause to Dr. Ariadne for giving us the nice speech. Ibu, actually, I still have so many questions for you because it's a very interesting talk, and we are actually very happy since you are our invited speaker who actually can present. And the other invited speaker, Dr. Fahabi, is in France, so its time difference is too long, so he cannot attend. So everybody who still has question for Dr. Ariadne, I think they can email you. Is that okay?
Yeah.
Yes,
please.
So please, to other participants who still want to talk or ask question, please send Dr. Ariadne by email. We will share your email, ya Ibu. We already have your information in our chat menu as well. So please do that. For now, I would like to invite everybody to turn on your camera because we will have a picture with Dr. Ariadne. Please, everybody, turn on your camera. Yeah, thank you very much. Dr. Vicky, can you please help us to take a picture?
Okay, ma'am.
Pak Ismail.
Okay, ma'am.
Sehat ya, Pak.
A lot of your students, ya Ibu, here.
Pak Ismadi.
Pak Ismadi. Be absent.
Good morning. Good afternoon.
Okay, Dr. Vicky.
Okay, I see there are 2 slides here, so we can begin from the first slide. Okay, 3, 2, 1. Okay, the second slide. Okay, 3, 2, 1. Okay, thank you.
Thank you very much, Dr. Vicky. Well, everybody, once again, let's thank Dr. Ariadne Juwono for joining with us this morning session. We hope to see you again, Ibu, next time, hopefully.
Thank you.
And everyone, now we have like a short break, only half an hour. Is that correct, Dr. Vicky? Yeah?
Yes, ma'am.
We will continue with the presenter session. We have 15 presenters who will present their paper. There will be 3 sessions after this, so we will start again at 12:30 in time. So I'll see you again in half an hour. Thank you very much, everyone.
Thank you, everyone. Good afternoon.
Thank you.
Good afternoon, Ibu. Thank you.
Sampai ketemu.
Sampai ketemu, Ibu.
Sampai ketemu juga, Ibu.
Ya. Izin live ya.
Silakan, Ibu. Terima kasih.
Terima kasih, sama-sama.
menghasilkan riset yang bermanfaat
Recording
bagi
in
rakyat
progress.
Indonesia. BRIN memiliki berbagai laboratorium, seperti Laboratorium Analitik dan Mutu, Laboratorium Biosafety, Ruang Bersih, Laboratorium Klinis dan Medis, Laboratorium Inkubator, Laboratorium Produksi, dan Laboratorium Penelitian dan Pengembangan yang tersebar di beberapa daerah. Memiliki laboratorium alam, di mana setiap lokasinya memiliki karakternya masing-masing. BRIN mengelola 5 kebun raya dan membina lebih dari 37 kebun raya daerah yang dikelola pemerintah daerah dan 3 kebun raya daerah yang dikelola perguruan tinggi yang tersebar di 23 provinsi.
Vicky, can we start the session?
Ini? Okay, I think we can start the session. Okay, thank you. Excuse me, Bu Dini, are you still mute?
Oh, sorry. Can you hear me now?
Yes, clearly.
Okay, thank you very much, Dr. Vicky. Welcome, everybody. I would like to introduce myself again. My name is Dini. I am from Research Center for Biomass and Bioproduct BRIN. Today, I am your chair, and I will lead for the sessions, also for the discussion session later on. So we are gladly to welcome 17 participants in this afternoon session that will be divided into 3 sessions. So there will be, like, for example, 5 to 6 participants in each session. We will first introduce your short bio, and then we will play your video recording. To my knowledge, everybody already sent your video. So after that, we can have a discussion like in that 3 break session, okay? So when we have the discussion, I would like to invite all of you to turn on your camera, because so we can appreciate our colleagues, ourselves, and we can have a more interactive discussion among us, okay? So for now, for the first session, I would like to first read the short bio from the first 5 presenters. Dr. Vicky, can you please help me? Our first presenter is Dian Anggraini Indrawan, who were born and raised in Bogor. Dian earned her bachelor and master degree from Institute Pertanian Bogor. She started working as a work program data analyzer and budgeting at Forest Research and Development Center in 2006 to 2009. She joined the Chemical Laboratory of Forest Product Research and Development Center in 2009 until March 2022. At the moment, she joined Research Center for Biomass and Bioproducts, National Research and Innovation Agency since March 2002. She has a research interest focusing on fiber technology such as fiberboard and pulp and paper. Our second presenter is Mr. Agung Sumorno, is researcher at the Research Center for Structural Strength Technology from BRIN. He graduated from ITB Bandung. Agung is now current researcher mainly on sustainable and green construction material. The third presenter is Lilik Astari, is a junior researcher at Research Center for Biomass and Bioproducts BRIN. She was graduated from Brawijaya University and the University of Melbourne, Australia for her master's. Currently, she pursues her doctoral degree at the University of Melbourne. Lilik's research topics are mainly on the development of particle board using agricultural byproducts and natural adhesive. The next presenter is Mrs. Debbie Mipasalam. Debbie Mipasalam is researcher at Biomass and Bioproduct Research Center. She graduated from Lampung University. Debbie's current research are mainly on wood science and forest product technology. The next presenter is Mr. Denny Purnomo, was born in Bandung, Indonesia. He is an engineer at the Biomass and Bioproduct Research Center of the National Research and Innovation Agency. He graduated from University of Mercubuana, Jakarta, and is now understudy magister at IPB University. Deoni Purnomo's current research is mainly on biocomposite engineering, design product, and drawing modeling. The last presenter for the session is Heru Suryanto. Is a lecturer, founder of the Center Excellence for Cellulose Composite, and editor-in-chief of Journal of Mechanical Engineering Science and Technology at the Department of Mechanical Engineering, University Negeri Malang. He graduated from University Brawijaya Malang. Heru Suryanto's current research is mainly on the cellulose fiber from both plants and bacteria and its nanocomposite. Is that all for the first session?
Okay, Bu Dini, it's the first session.
Thank you. Now, everybody, we will listen to their video. Please pay attention, and you can also discuss. We can discuss later on in the discussion session. Thank you, Dr. Vicky.
Thank you, Bu Dini.
Good afternoon, everyone. Allow me to introduce myself. I am Dian from Research Center for Biomass and Bioproducts, National Research and Innovation Agency, Indonesia. In this opportunity, I would like to present research titled Hardboard Quality of Mixed Sisal, Gelagah Grass, and Empty Palm Oil Fruit Bunches. Let me start by giving you some introduction to this research. Wood is a fiber material commonly used to manufacture fiberboard, including high-density fiberboard or hardboard. However, the wood supply from natural forest is dwindling due to the increasing forest degradation, reducing the world's forest area. Deforestation and forest degradation, loss of biodiversity, and climate change are the three significant crises affecting forests worldwide. Legality issue of the wood as raw material received serious attention related to the environmental impacts. So it is necessary to find alternative fiber sources that can be used for hardboards. Several alternative non-timber sources that can be used because of their great potential are sisal, gelagah grass, and oil palm empty fruit bunches. All three sources include lignocellulosic fiber materials, so they can technically be used for hardboards. So now let's move on to material and methods. The materials used are as below. And the following are some of the methods used. The raw materials are manually cut into 5 cm in size, then dried in the open or under the roof until it reaches the air dry moisture content. Then the dry fibers are ready to be cooked into pulp. The raw material is separately processed into pulp using an open hot semi-chemical soda process in a cooking kettle with a capacity per batch of 1000 grams oven-dried flakes. The ratio of the raw fiber to the cooking solution of 1:8, maximum cooking temperature 100 degrees Celsius for 2 hours. The alkaline concentration were 9% and 10.5%. The soft fibers were then separated into separate fibers or pulp on a Hollander beater at a consistency of 3 to 4% for 1 hour. The obtained pulp is then reduced in water content using a centrifuge. Then the yield is determined. Each pulp obtained was mixed with each other at certain proportion for hardboard formation. Fiber material in various proportion of mixtures was formed into hardboard using a wet process. And the following is a picture of the hardboard manufacturing process in the lab. The following is the composition and proportion of fiber stuffs and additives for the forming of hardboard mat. Additives added are tannin formaldehyde, wax emulsion, and alum. And the following are the tests carried out on raw materials and hardboard. Next, I'd like to move on to result and discussions. Moisture content, density, and chemical composition of raw material. The calculation data of moisture content, density, and chemical composition are presented in the table. It can be seen that the highest water content was owned by sisal, followed by oil palm empty fruit bunches, and the lowest was gelagah grass. According to GIS, the water content value of the three raw materials were still classified as low. Glaga grass has the highest density value, followed by sisal, then oil palm, empty fruit bunches. This density value is related to the amount of parenchyma tissue and extractive substances, as well as the chemical composition of raw materials such as lignin, alpha cellulose, and silica content contained in each raw material. The highest alpha cellulose content in the three raw materials was found in glaga grass, oil palm, empty fruit bunches, and then sisal. While for the highest levels of pentosan were sisal, oil palm, empty fruit bunches, and then glaga grass. Different to pentosan, the highest lignin content was owned by oil palm, empty fruit bunches, glaga grass, and then sisal. Cellulose, lignin, and pentosan play important roles in the manufacture of hardboard because cellulose itself is a constituent of fibers. Lignin can bind among fibers, while pentosan facilitates the grinding process and has good strength when mechanically treated. The highest S content was oil palm, empty fruit bunches, glaga grass, and sisal respectively. As for the silica content, the highest value was owned by glaga grass, oil palm, empty fruit bunches, and sisal. Hence, from this data, sisal has the lowest S and silica content than the others. This causes a positive effect on the prospects for sisal raw material due to interference with metal tools, which are more easily blunted, and the bond between fibers on the hardboard will be reduced. Fiber dimensions and derivative values. Based on table, it can be seen that the three raw materials had different fiber dimensions and derivative values. Glaga grass had the longest fiber dimension and the largest diameter, while the shortest fiber belonged to oil palm, empty fruit bunches. The fiber diameter of oil palm, empty fruit bunches, and sisal were not different significantly. The fiber length is thought to affect the breadth and width of the fiber more intensively during the formation of the hardboard, and the long fiber can increase dimensional stability during water absorption and removal. For lumen diameter, glaga grass also had the largest diameter, followed by oil palm, empty fruit bunches, and sisal. Meanwhile, sisal has the largest melting power than glaga grass and oil palm, empty fruit bunches, with a considerable difference. The highest value of flexibility coefficient, stiffness coefficient, and mole step number was owned by glaga grass and sisal. Longer fiber, thinner fiber wall, larger diameter and lumen fiber, higher felting power and flexibility ratio, and lower wrinkle ratio, rigidity coefficient, and mole step ratio are desirable because all of these are closely related to the flattening, flexibility, and felting properties of the fiber, so that it has a positive effect on the quality of the pulp and hardboard product. Physical and mechanical properties of hardboard. From the table, it can be seen that the water content meets the requirements of the GIS and ISO standards, while the thickness, swelling, and water absorption do not meet the standard requirements. In terms of density, all of them meet GIS and ISO standards, while for MOE, MOR, and internal bond only, some meet the requirements. Hardboards made from 100% sisal and 50% sisal plus 50% glaga grass have the highest value of moisture content, thickness, swelling, and water absorption, while the lowest were found in hardboards made from a mixture of 50% glaga grass plus 50% oil palm, empty fruit bunches, and glaga grass plus oil palm, empty fruit bunches plus sisal 33.33% each. These three hardboard characteristics are related to the hydrophilic nature of the compound content of the raw materials and the remaining fat or oil contained in the raw materials. For the MOE value, the highest level was found in hardboards made from 100% sisal, which was allegedly caused by the high cellulose content in sisal. Then for MOR and internal bond hardboard, the highest value is owned by hardboard with a mixture of 50% oil palm, empty fruit bunches plus 50% sisal. This is due to the high felting power of sisal fibers and the rigidity coefficient of oil palm, empty fruit bunches plus glaga grass and sisal 33.33% each. For the highest heat conductivity with the lowest heat resistance, hardboard is made from a mixture of oil palm, empty fruit bunches plus glaga grass plus sisal 33.33% each, which is allegedly caused by the high felting power of glaga grass and sisal fibers. and the thin walls of oil palm empty fruit bunches and guava grass fibers, while the lowest thermal conductivity with higher heat resistance is owned by hardboard made from 50% oil palm empty fruit bunches plus 50% sisal as raw material. This is allegedly due to the high fat or oil content in oil palm empty fruit bunches and low lignin content in sisal. Additives, especially tannin formaldehyde adhesives, can move into the fiber structure and fill the voids between fibers, while wax emulsion can also increase water repellency so that the hygroscopic nature of the hardboard decreases and the dimensional stability of the hardboard increases by disrupting the contact and bonding between the fibers in the hardboard. Crystallinity analysis using XRD instrument on fiber materials showed the highest crystallinity is owned by sisal fiber, followed by guava grass and then oil palm empty fruit bunches. The crystallinity value of a fiber material is allegedly related to the individual strength of the fiber. The higher the crystallinity, the higher the fiber strength, which is also expected to be positively related to the strength properties of the hardboard. However, based on discriminant analysis, the results obtained are inversely related to that this possible occurs because aspect of the basic nature of the fiber, pulp processing and hardboard products beat the crystallinity strength of the material. In conclusion, let me sum up the main points. The order of the roles of each physical property strength of hardboard products on product quality is MOR, MOE, internal bond, density, thermal conductivity, heat resistance, thickness expansion, moisture content, and water absorption. The individual potential fibers for hardboard are oil palm empty fruit bunches, guava grass, and then sisal, the last. And in the form of mixed fiber for hardboard, the order of the most potential proportion is oil palm empty fruit bunches 50% plus sisal 50%, followed by guava grass 50% plus sisal 50%, and sisal 100%, and guava grass plus oil palm empty fruit bunches plus sisal each 33.33%. That's all my presentation, and thank you.
My name Agung Sumarno. I'm from Research Center for Structural Strength Technology, National Research and Innovation Agency. I would like to present our research about thermal analysis and solution of green cementitious composite model under constant and elevated temperature. Background: several nations in the world are not only dealing with population growth but also confronting the climate change following the temperature rising across the globe. Previous study explored concrete or lightweight concrete behavior under elevated temperature, studied concrete thermal properties or behavior of concrete during curing under ambient temperature to emphasize the importance of including the concrete thermal performance in research before implementing in the field. However, in building analytical modeling of concrete, especially those composed with natural fiber, is still lacking, and combining the effect of constant and elevated temperature on green concrete unit is also overlooked in the previous work. Objective: to understand and to compare the thermal distribution of green cementitious composite made from 7 fibers under ambient and elevated temperature. 2 models are considered in this study: solid block and hollow block, or a block with cavity. Object of study: the object of study is illustrated in figure 1. 7.5 cm thin exterior wall unit constructed from a green cementitious composite. This study adopt a hybrid design of resident house as shown in figure 1. Lightweight cementitious composite like green concrete usually provide a lower compressive strength that reduce the load that can be carried by lightweight walls. in order to assure the structural safety as well as the thermal behavior of the green concrete composite wall, reinforcement should be detailed and also considered in the analysis. Therefore, in the thermal analysis conducted in the study, a single unit of concrete block is considered instead of a clear wall unit to simplify the analysis and to understand comprehensively the thermal behavior of a single concrete block unit. Thermal model. A solid element in figure 2 experience a steady state one-dimensional head conduction following equation 1. The head transfer is expressed following equation 2. Therefore, following equation 1 and equation 2, the overall model can be stated as per equation 3, in which for the limit closer to 0 and the value of is assumed to be constant, resulting in equation 4. The model dimensions are 60 by 20 and by 7.5 cm, expressing the length, height, and thickness of the unit. The effect of the cavity is compared to the solid model under constant and elevated temperature. Material properties of green cementitious composite in this study are based on 7 test results adopted from previous study as shown in table 1. Various properties of the green concrete fiber are considered, from natural fiber M1 to M4 to steel, plastic, and glass fiber, the density ρ and thermal conductivity K are modeled to find the solution under steady and transient state for both temperature condition. Boundary condition. For steady state condition, the thermal wall surface temperature is subjected to an ambient temperature of 28 degrees Celsius. For the transient state condition, a similar assumption is adopted with a final time of 120 seconds. Only the external and internal surface of the model are subjected to temperature, while the top and bottom surfaces are assumed to be insulated. The thermal model is meshed with a size of 0.005. The solid model adopts the actual size of the concrete block with a height of 20 cm and thickness of 7.5 cm. The model with cavity also uses the similar dimension with a rectangular cavity with area of 10 by 10 mm square is added to reduce the effective area. Only single material is used to constant the exterior wall. For the constant temperature model, the thickness is considered from x0 to dx 0.075. Result and discussion. Constant temperature. The steady state model developed here is used to verify the transient state result. Model validation is analyzed at the center of the model. The temperature distribution and gradient between the two conditions are similar. For the solid model, the temperature distribution inside the unit is more varied when vermiculite, palm, and hemp fiber are used. Seagrass hold the head distribution more uniformly. as compared to other natural fiber model. Meanwhile, the plastic, steel, and glass model distribute the ambient temperature from exterior wall more evenly due to their higher conductivity. The effect of a small cavity with a size 10 by 10 mm square shows the effective distribution area is reducing by the cavity. Using vermiculite fiber may provide the highest approximate temperature loss of 4.13% as compared to other natural fiber model. However, the natural fiber still perform better than plastic, steel, and glass fiber. Under elevated temperature, 7 models are analyzed under elevated temperature that is determined as 600 degrees Celsius, which the heat source at the inside of the wall. The temperature distribution or gradient between the two conditions are also similar. Vermiculite, palm, and hemp fiber still show a non-uniform distribution of the heat from inside surface to outside surface of the wall. The plastic, steel, and glass model also still distribute the elevated temperature from interior surface to exterior surface of the wall more evenly due to their higher conductivity. The effect of small cavity with size 10 by 10 mm square is also explored for the elevated temperature solution. Similar to constant temperature solution, using vermiculite fiber also provide highest approximate heat loss of 36.49% as compared to natural fibers model. Natural fibers still perform better than plastic, steel, and glass fiber. Conclusion: natural fibers as adopted in this model lead in thermal performance as compared to either plastic, steel, or glass fiber. Temperature and heat loss for plastic, steel, and glass fiber are almost identical, showing that uniform distribution of heat is experienced inside each unit with very small temperature and heat loss. Meanwhile, vermiculite, palm, and hemp fiber experience non-uniform distribution inside the model, providing higher loss of temperature and heat on the models, either under constant or elevated temperature. Using vermiculite fiber in the analytical solution shows better performance as compared to other natural fibers model or plastic, steel, and glass models. The temperature loss of vermiculite fiber is approximate as 9.32% under constant temperature, while 36.49% of heat loss is computed when vermiculite model is analyzed under elevated temperature. Thank you for your attention.
I'm Lily Astari. I would like to present our research with the title Surface Roughness and Mechanical Properties of Particle Board Made from Alang-alang and Sorghum Stalk. This research is collaboration between BRIN Indonesia and IBB Unity. The outline of my presentation today, so it will begin with the introductions, followed by material and method, and continue by results and discussions, conclusions, and future research suggestions. So global production on particle board, including oriented strand board and fiber board in 2020 was around 250 million meter cubic according to FAO. This amount was 109 increase compared to the production in the last decade. The driver of this growth is our economic development and also the growth of the populations. So the particle board, as you can see in the picture, are commonly used as the main component on furniture and structural. So particle board has a wide range of the advantages, such as it is affordable, it is lightweight, and it can be applied in various specification products. However, there are challenges and opportunities in the particle board fabrications. The challenges are mainly on the restriction on petroleum-based adhesive in regards to the conventional adhesive that commonly used, which are urea formaldehyde or UF and phenol formaldehyde or PF, and also a challenge on the shortage on the wood chips. However, there are also opportunities in Indonesia, which has abundant on non-wood lignocellulosic sources, including agricultural byproducts and annual plants. These non-wood lignocellulosic sources are opportunities to substitute wood chips as the raw material for the particle board. Alang-alang or cogon grass or Imperata cylindrica are wild plant and annual plant that widely grow in Indonesia. Sorghum or sorghum bicolor also agricultural plantation that currently widely planted in Indonesia. With the wide plantation area, it consequence to the high amount of agricultural byproducts. These two biomass are an potential biomass to be utilized as the substitution for the wood chip for particle board fabrication. So the aims of this research are to investigate the suitability of alang-alang mixed with sorghum and formaldehyde-based adhesive for particle board, and to investigate physical, mechanical, and surface roughness of particle board made of alang-alang and sorghum, and also to contribute to the value added of alang-alang and sorghum stalks. So this is the material and method. Alang-alang and sorghum were collected from Cibinong area, Bogor, Indonesia. And the adhesive that we used were phenol formaldehyde and urea formaldehyde, 10% of the dry weight of particle. So this is the process that we conducted. First, the biomass were chopped and processed using ring flaker to obtain particle, and then the particle sieved to gain 4 to 14 mass, and then the small particle often dried to obtain moisture content less than 5%. And then we weigh the particle and the adhesive according to the formula, and then we mix the adhesive, and then the mixture go to the hot press with a different pressing temperature, which were 150 degrees Celsius for the particle board using PF adhesive and 130 degrees Celsius for the particle board using UF adhesive. The pressing time were 10 minutes with the pressure around 25 kilogram force per centimeter cubic. After hot pressing, all the particle boards were conditioned in a room temperature for 7 days. After 7 days conditioning, all the boards were cut according to sample test dimensions. The tests were conducted for its physical, mechanical, and surface roughness tests. So for the physical properties test, including moisture content, water absorption, and thickness swelling tests. For the mechanical properties, we measure the flexural strength, including MOR, MOE, and also we measure the internal bond and the screw withdrawal. And also we measure the surface roughness of the particle board, the surface roughness average or RA. Results and discussions. The moisture content, as you can see at the left side of the screen, shows that particle board with PF perform better moisture content, which is between 6.3% to 10.85%. This is also confirming that PF is more suitable to be used for outdoors purpose products. The density of the particle board in this study were between 0.88 to 0.95 gram per centimeter cubic. These values are in the range of the required standard, which is 0.4 to 0.9 gram per centimeter cubic. Particle board in this study is considered as high density particle board. For the thickness swelling, again, particle board with PF shows the less swelling and absorption. The best value for TS is 28.84 with the better absorption 43.99%. This value is still below the standard, therefore improvement for water resistant properties for this particle board are needed. For the mechanical properties, all type of particle board are fulfilling the GIS requirement. The least MOR value in this study was 9.33 MPa and the highest is 25 MPa, while on MOE value, only particle board with urea formaldehyde adhesive and more amount of sorghum meeting the standard. For the internal bond properties, which is measure the tensile strength of the material when applying a force perpendicularly, the more amount of sorghum particle with urea formaldehyde adhesive show the better value. And for the screw holding power, even though the trend show increasing value on the more sorghum particle, yet it's still not satisfying the minimum requirement. For the surface roughness properties, the value of RA are above the literature range. In this study, the range of the surface roughness average were 7 to 14.1 micrometer, while the commercial range were between 3 to 6 micrometer. Particle board in this study means that it needs to be further sanded after the productions. So the conclusion of this research is ratio of alang-alang and particle and types of adhesive significantly affect the physical and mechanical properties of the board. The value of density and moisture content of the particle board are fulfilling the standard. The higher ratio of sorghum particles in the particle board, the better result on the mechanical properties. Particle board types D, which is 75% of sorghum, and E, which is 100% of sorghum, perform the higher results. Overall, particle board types D and E with PF adhesive provide the desirable properties. The surface quality of the particle board in this research are out of the common commercial range. Thus, the modification of the finishing techniques for the particle board in this study are necessary. Future research suggestions or investigation on chemical properties of alang-alang are needed. The development of particle board made from alang-alang and sorghum using non-formaldehyde adhesive are worth to be investigated. Incorporating alang-alang with another agricultural byproduct which widely spread in Indonesia for higher value added biocomposite products are also need to be investigated. So this is bring to the end of my presentations. Thank you very much for your attention.
Assalamualaikum warahmatullahi wabarakatuh. Thanks for the opportunity and time that has been given to me. I will present the result of our research on potential benefits of the pterocarps resin as a basic utilization for functional usage. The members in this research are Debbie Mipasalam, me, Aulia Nurlaksmita, Andrian Fernandez, and Rizky Maharani. There are a large number of genera that one can find in the family of Dipterocarpaceae. The genera of this family are found to be distributed in Indomalaya regia, i.e. Triobalanops, Sorea, Eupina, Parasorea, Anisoptera, Neobalanocarpus, Cotylelobium, Hopea, Fatica, and Dipterocarpus. Each genus from Dipterocarpaceae has several distinctive characteristics such as the exudate, Plants can produce exudate that usually comes out when the plant gets cut and is going to be hardened when it comes in contact with air. There are many types of exudate, and the most common types of it are resin, latex, and gum. The genera of Sorea and Vatica have resin as their distinctive characteristic. Traditionally, the local people use resin or Oreo resin as fuel to light up torch or fire. Although resin actually has so many more utilities. Example, as an ingredient for traditional medication. The chemical substance of resin that is contained in Sorea leaves and Vatica Rasak had not been discovered, which means that it needed to be tested using phytochemical and GCMS tests. So, the research was conducted in order to discover phytochemicals and active compound contained in Sorea leaves and Vatica Rasak from natural tourism area of Bukit Bangkirai, East Kalimantan. Materials and methods. Sample preparation. Resin of Sorea leaves and Vatica Rasak was obtained from making scars on the trees. Phytochemical tests have 4. The first alkaloid, flavonoid, saponin, and the last is tannin test. GCMS test was carried out to estimate the compounds contained in the extract. Results and discussion. Result of phytochemical test. According to the phytochemical test, alkaloid was contained only on resin of Vatica Rasak. Alkaloid is heavily used in medication because of its pharmacological effects such as inflammation, antibacterial, antitumor, and EDC. Flavonoid and saponin was found in Sorea leaves and Vatica Rasak. Flavonoid functions as an antioxidant and saponin that is presumed to be useful as an antimalarial medicine and antioxidant. Tannin was not found in the Sorea leaves and Vatica Rasak. GCMS test results of both resins, both of which have globulol compounds. The function of globulol is prevenociseptic, as in cancer, antibacterial, anti-cancer, antifungi, antioxidant, ADC. Globulol was found in the retention time 20.985 on Sorea leaves and 24.367 on Vatica Rasak, with concentration on Sorea leaves 2.88% and Vatica Rasak 3.55%. The second compound is caryophyllene oxide. The function is anti-cancer, anesthesia, also anti-inflammatory agent. Third compound is aromadendron oxide. The function is antimicrobial, useful in epidermoid skin cancer, precancer cell medication therapy by combining it with caryophyllene. The last compound is isoaromadendron epoxide. The function is antibacterial, a protection from UV light, antifungal, and the last is anti-inflammatory agent. The following are compounds found only in Sorea leaves, i.e. spatulenol, andrograpolite, humulane 1.6-3-ol aristolene epoxide, and aromadendron oxide 1. And the Vatica Rasak only is caryophyllene, 3-cyclohexane 1-carbosaldehyde, 3,4-dimethyl, 2.6.6.10 tetramethyl undeca 8, 10-diene, 3.7 dione. The conclusion is phytochemical test from Vatica Rasak is known to have alkaloid, flavonoid, and saponin with moderate concentration. And Soria leaves was not contain alkaloids, but it contained moderate concentration of flavonoids and high juice concentration of saponins. Resin of Vatica rasa contains several compounds from the one that has the high juice concentration, which is caryophyllene oxide 2.6.6.10 tetramethyl under 8, 10, diene 3.7 dione, 3 cyclohexane, 1 carbosaldehyde, 3.4 dimethyl, caryophyllene isoaromadendron epoxide, globulol, isoaromadendron epoxide, and aromadendron oxide. From the result of GCMS, these two resins have great benefit as medicinal plants that can be used as basic research to newly discover various potential benefits of both resin for development of the functional product possibility. And the last Soria leaves showed that it was presumed to contain humulene 1.6-diene-3-ol, aromadendron oxide, 1-spatulenol, androgapolid, aristolene epoxide, caryophyllene oxide, globulol, isoaromadendron epoxide, and aromadendron oxide 2. Okay, thank you. Wassalamualaikum warahmatullahi wabarakatuh.
It is my honor to present our study at the International Conference Lignocellulose. My name is Jennifer Domo. I would like to present with the title Physical and Mechanical Properties of Fiber using polyol isocyanate adhesive binder for insulation material. Environmental issues for the use of wood as an industrial raw material are currently on the rise. Lignocellulosic fiber are now one of the hot topics in the field of study. The primary component of the lignocellulosic material are cellulose, hemicellulose, and lignin. Together with another component, according to Java 2014, can be used as a subtitle material from the coconut agricultural production or waste as a raw material can be used by the industry as a non-wood raw material to meet the market needed. Coconut fiber is the one of natural fiber as the alternative raw material that is very easy and very cheap. There have been many previous studies that have analyzed the physical and the mechanical properties where the coconut fiber have a wide variation in the cross section of the fiber length against modulus elastis and modulus rimmer and modulus young, which after their mechanical properties according to Bakri 2010. One of the most adaptable volumetric material is for adhesive, of course, is a polyurethane foam, which has a great abrasion resistance and hardened and chemical and solvent resistant. So the natural fiber are very abundant in Indonesia. Coconut fiber is used as an insulation composite for wall filler. In general, still use non-natural materials such as glass wool, polyurethane, fiberglass, polyamide foam, and the other. There is research to analyze the quality of the fiber, both physical and mechanical properties. This advantage of the synthetic insulation material as easy falling out, cause skin irritation, and cause the respiration problem, is according to Debical et al. 2020. So this material for this studies, coconut husk fiber, can be purchased from local business in Sukabumi, West Java, with the moisture content under 13% for polyurethane adhesive and the metal chloride, which are used to create the fiber board as insulation, can be purchased from PT Anugerah Raya Kencana dan Mogot. So the variation, the pattern to making insulation board, the size to 10 centimeter and 120 centimeter with the thickness 5 centimeter, with the formulation 8% fiber and 20% adhesive, with 4 variation. So the coconut fat fiber and adhesive, we weighed it and then we mix, then sprinkle on the molding by manual hand layup, and then pressing using the cold press for 2 hours to make the fiberboard adapting the GIS A5905 2003 insulation board. Then this is the result and the discussion to determine the density. We calculated using the formula the density value of a coconut fiber with low density result for variation as shown in the figure. Coconut fiber board may still meet the GIS A5905 2003 standard for insulation board, which is below 0.35 gram per centimeter cubic. For the result density variation with the formulation and adhesive content, fiber show that the technique showing fiber in the molding use hand layup is a significant effect on the homogeneity of the flatness of the board. From the morphology result to the dimensional analysis with the Keynes digital microscope with 20 times magnification, it can be seen that the homogeneity of the fiberboard from the color photo microscopic show that the high and low surface in scale micron. So the manufacture of low density insulation board is taken high variation fiber that and then bulky when printed. Why is taken the high variation? Because the expected target of the board with low density vertical board is influenced by the structure of physical from the raw material vertical use. Vertical type, felt ratio, number of vertical, and then number of adhesive and additive is a factor that affect to density value according to Keeley 1097. So from the figure moisture content, it can be seen that the large moisture content is 11.9% at the fiberboard density 0.06 gram per centimeter cubic. That is the highest, and the density 0.1 gram per centimeter cubic. That the low moisture content is 2.33%. With increasing density, the water content of the coconut fiber board is decreased. When the condition to remove the strain do flattening, and in oven room and the room temperature, it has a hygroscopic properties of absorption or releasing the water air from the surrounding environment, filling the void of vertical cavities between the fiber, according to Perwanto 2018. So the result for water absorption, so the level of water absorption causes the physical properties of the raw material and the adhesive properties used in this study of adhesive using polyurethane will increase the value of thickness development by previous studies. In addition of the level density types test sample is also from the result of analysis has a marked effect on density level 0.04 and 0.1 gram per centimeter. It's still having water absorption of 91.5 and 93.39 as shown in the figure. This can be caused by the porosity of the test sample and the smaller coconut fiber vertical size filling. So the thickness swelling as shown in the figure, that influence of the result of the data analysis is not all high density result as a lower thickness development value of a vice versa. This could be possible due to the homogeneity of the distribution of fiber vertical or adhesive. In this study, density variation has no real effect judging from the table on NOVA analysis data, thickness swelling density 0.04 and 0.1 are 2.78% and 3.25. So the density is 0.06 and 0.08 are 3.30 and 4.25%. However, still meet the standardization. So for the modulus elasticity that remain below standardization of the GIS, which is less than 2 Newton per millimeter, and then the value of bending constancy of coconut fiber, namely increasing by the density and the elasticity modulus from 0.06 Newton per millimeter from density of 0.04 to 0.25. As shown in the figure, that the test value modulus rupture is 0.0559 Newton per millimeter. So the result testing coefficient of the velocity can be seen that influence of density that has a significant effect on the strong result of MOE and MOR. As the additional data, the standard flammability test customer refers to FMSV test method 302-2006 implemented in the Republic National Research and Innovation Agency with the dimension 300 to 100 millimeters with the thickness 45 using the U-Safe flammability test tool sample. And then in the horizontal combustion direction, with the duration 48 hour initial combustion of 15 seconds that we can show in the figure, the flammability test condition show the result from the four variation on the morphology that describe of the result of the after initial combustion. The test result with the value of the burn rate millimeter per minute. The coconut fiber insulation board with the polyurethane binder is not flammable if a self-extinguished fire doesn't dies before the measurement limit. So this is possible due to the composition of the adhesive polyurethane is very high. So because the polyurethane itself is not flammable, involvement coconut fiber. So for the conclusion in this study, coconut fiber insulation board did not all characteristics meet the standardization of GIS. Mechanical property have not met requirement, but physical purposes such as development, thickness, density, and the water absorption still meet the standardization. So the density variation have a significant effect of the quality value of the coconut fiber insulation board. And then for the next study, maybe to be met according to the standardization is recommended to increase the density value and the treatment to the fiber. So the coconut fiber insulation board is more optimal as surface conductor reach. I think that's it for our presentation, and then this is the reference that we use. Thank you very much for your attention.
Assalamualaikum warahmatullahi wabarakatuh. Greeting to all. I introduce myself. My name is Heru Suryanto from Department of Mechanical Engineering, Universitas Negeri Malang. I will present our paper that detail the influence of coupling agent on interfacial shear strength of Sansevieria cylindrical fiber epoxy composite. The need for strong, lightweight, environmentally friendly, and economical material increased rapidly in last year. Natural fiber is the fourth essential as fiber reinforcement in polymer composite due to its excellent mechanical properties. The properties could be improved through modification on the fiber surface. The use of silane coupling agent could increase the adhesion between natural fiber and epoxymatic by modifying the surface of natural fiber. Current study aims to determine the influence of the concentration of silane coupling agent on the composite interfacial shear strength of acylindrica fiber in the epoxy composite. Current research, we use material Sansevieria cylindrica fiber age 6 to 8 months, sodium hydroxide, silane coupling agent KH560, ethanol, epoxy resin, and hardener with epoxy brand. Fiber rating was conducted mechanically by heating the stem of acylindrica in wet condition repeatedly. Fiber that clean and water until it detached from tissue and then dried at room temperature. Alkalization process was done by soaking the fiber in 5% sodium hydroxide solution for 2 hours. Fiber then rinsed with water 5 times and dried in room temperature. Silane coupling agent with various concentration 2.5, 7.5, and 10% were added to ethanol solution. Fiber then immersed into the solution and homogenized using ultrasonic wave 20 kHz, 300 watt for 50 minutes, and washed using distilled water. Fiber then dried in oven for 2 hours at 75 degrees. Fiber surface morphology was observed using scanning electron microscope type inspect S50. Fiber structure analysis was conducted using HRD pan-analytical type expert probe. Diffraction used 2 theta in ring of 10 to 60. Degree of crystallinity and crystallinity index was calculated using Segel equation. Interfacial shear strength were calculated from pull-out test. Pull-out test conducted by mixing the resin to hardener with ratio of 2 to 1 and pouring into mold. Treated fiber was embedded into wet epoxy slowly with a depth of 0.2 millimeter and left it until hard. Single fiber pull-out test carried out using fiber tensile tester with a maximum load of 50 Newton, 5 samples for each treatment. Okay, we can see the result of silane treatment. At a fiber contour looks smooth. Then after silane concentration, surface fiber looks more rougher. The rougher of the fiber surface linear with addition of silane concentration. Silane treatment caused the surface fiber become rougher due to deposition of silane on the fiber surface. Crystallinity analysis using HRD indicate that there are 3 peaks located at diffraction angle of 16.6 degree, 22.5 degree, and 34.7 degree. That indicates crystalline structure of fiber with crystalline plane of 011, 002, and 500 respectively. These crystalline planes are strongly associated with cellulose type 1. Segal formula to calculate the crystallinity of fiber after treatment indicate that degree of crystallinity and crystalline index of control fiber 49% and 66% respectively. The crystallinity is increased after treatment of silane. The highest crystallinity and crystalline index presented in silane coupling agent 10% with percentage of 66% and 75% respectively. Pull-out test analysis indicate that interfacial shear strength of each treatment shows a different result. Increasing of silane concentration, increasing interfacial shear strength epoxy fiber. Treated fiber with silane makes fiber have hydrophobic surface, so compatible with hydrophobic polymers like epoxy. Silane coupling agent change the hydroxyl group into silanol group that result in increment of binding between matrix and fiber, so the interfacial shear strength also increase. Interfacial shear strength on the raw surface is more effective due to the mechanical interlock mechanism. Increasing crystallinity and fiber makes interfacial shear strength increase too. Addition between fiber and epoxy increase with increase of crystallinity. The conclusions of research: fiber specimen with silane coupling agent concentration with a concentration of 10% have a rawer structure. SRD analysis show that fiber indicate 3 peaks at 2 theta, 16.6 degree, 22.5 degree, and 34.7 degree. These peaks are strongly associated with typical cellulose 1. As cylindrical fiber structure with silane coupling agent concentration of 10% has the highest crystalline structure. The addition of silane coupling agent increases the shear strength of the composite interface of cylindrical fiber epoxy, and the highest interface shear strength value of 91.3 to 1 megapascal obtained from the treatment of silane coupling agent of 10%. Thanks to LPPM Universitas Negeri Malang through publication grant 2022. Thanks for all. Assalamualaikum warahmatullahi wabarakatuh.
Okay, that was the first presenter from the first session. Now I would like to invite all the presenters to on camera. Could you please turn on your camera, and then so we can have an interactive discussion among us. I would like to invite Ibu Dian, Miss Dian, Mr. Agung, Miss Lili, Miss Debbie, Mr. Denny Purnomo, and Mr. Herius Suryanto. Yeah. Is there anyone who would like to ask a question first? Maybe can raise hand.
Excuse me, Budini.
Yes.
I think there is a question in the chat room.
Okay. I will check. Okay. This question is for presenter Miss Lilik Astari. The result of research on particle board from alang-alang and sorghum are suitable for what raw materials? I think the question is for the product, I guess.
Yeah.
Can you please
Okay,
answer first? Yeah.
Budini, can you hear me?
Yes. Yes, Lili.
Yeah, okay. Yeah, thank you very much for the question to Pak Suroto, to Mr. Suroto. So, our aim for this product is as the raw material for the furniture, for the interior purposes material. And but looking at the adhesive that we use, we're looking for the two possibilities. So either for using UF or PF.
But regard to the physical properties, especially the thickness swelling, which is the crucial characteristic of the particle board, unfortunately, it still needs a lot of work because, as you can see, that the thickness swelling, the lowest one, still 23%, which the requirement requires 12% as the maximum one. But if we look at the mechanical properties, we can reach 25 megapascal, which the minimum is 8 megapascal. So we're confident that with more improvement in additives such as water repellent, so this material will be suitable for raw material for the furniture purposes. I hope this answered the questions for Pak Suroto.
Pak Suroto maybe can give a comment, or if it's enough.
Thank you, Miss.
Okay.
Lily.
Okay. Thank you for your question.
I think Mr. Tio and Mr. Denny Promo need to wait because there's another question for Mr. Lilik Astari. So just I will read that. I will read the question. Have you ever calculated the economic value of particle board and sorghum for industrial purposes? Because as we know, both of them are volumetric material.
Okay. Thank you for your question to, I think, Ms. Rizky. Yes, it is very, as you know, the fabricating particle board from agricultural byproduct is a massive preparations effort at the beginning. So from the collection from the farm, so there will be actually two big works. So the preparation of particle itself, it should be different from the fabrication itself. So it should be also the considerations when we fabricating particle board using agricultural byproduct and especially using the natural adhesive. But in our work, we're still using the formaldehyde adhesive. We haven't calculated yet for the economic value, so we're still concerned on the development of the process itself. But your question is very good idea for us. It's very good suggestions of how to calculate the economic value, because yes, it is. It's a massive work on the preparation of the fabrication of particle board, and the raw material is very bulky. And yes, we need to look at the economic value and the feasibility of fabricating particle board using the alang-alang and the sorghum. But looking at the properties, we have like green light. We have a very good insight in the characteristic, and for the economic value, we still need to work on it. Thank you very much. I hope this is answering, and thank you for your input.
Thank you, Ms. Lilik. Bu Rizky, Ms. Rizky said enough.
Yes, enough. Yes, it's just for input, of course, because it's very important. Yeah. We will going to go with industrial purposes. Then it's very important. Yeah. Thank you, Ms. Lilik. Good luck.
Thank you, Ms. Rizky. Thank you for your input.
Okay, the next question will be from Mr. Kurnia Wiji Prasetyo, please.
Thank you, Mr. Dini. I would like to make my question for Bu Dian Anggraini. Next presentation. You research, you use non-wood fiber. This is a very interesting research. So how to measure about the slenderness ratio, compression ratio, of fiber in this research to influence the physical and mechanical properties of hardwood, because the fiber from non-wood is maybe different with article from hardwood or softwood. Maybe how to measure the effect of slenderness ratio and compression ratio from the fiber for the physical and mechanical properties from hardwood that already you manufacture. Thank you, Ms. Dini.
Thank you, Mr. Kurniawiji. Can please Ms. Dian to answer directly to the question, please? Ms. Dian, are you here? Are you present?
Excuse me, Bu Dini.
Yes.
I think Mrs. Dian is, but there is the counter, Mr. Gustan Pari.
Professor Gustan Pari.
Professor Gustan Pari.
Please, Prof.
Yes, I'm sorry, Mrs. Dian is now lecture in the IPB. So he said to me, sorry, he cannot be the answer, but thank you very much, Dr. Kurnia, for this question. So maybe is the difference between wood composite wood fiber and the material from the wood and from non-wood fiber. Then because we compression ratio, we add to based on the standard of wood fiber. So maybe we can make the standard about the composite of fiber wood from the non-wood material. Is maybe we can join together. We make the new standard of the non-wood fiber composite.
Okay, thank you, Prof. Mr. Kurniawiji, is that
nice idea, Prof. Gustan? Maybe.
So there is no standard SNE for the particle board from non-wood.
Because in particle board standard ratio is more minimal, is 150 points. Right. So maybe in non-wood fiber we can get new standard.
Right.
Thank you, Mr. Gustan. Thank you, Mr.
It will be a good project for making a new SNE for the particle board from non-wood, Thank you, Prof. Gustan Pari and Mr. Kurniawiji. And then we have also a raised hand from Mr. Denny Purnomo, please, to ask the question.
Thank you very much, Dr. Denny. Very nice presentation. I would like to have a question for Ms. Lily and Mr. Agung. For Mr. Agung, have you already compared or followed thermal model with the thermal conductivity test? And for Ms. Lily, because the product is output for industrial product and the adhesive using VF. So how about the formaldehyde helium? Okay, thank you.
Please answer directly, Ms. Lily.
Okay, thank you, Mr. Denny. My voice is it clear? Because this is in my house very heavy rain. Is it clear, Mr. Denny? My voice?
Yes, it's very clear.
Okay. In this research, we use a numerical model to predict how the concrete composite can be reduced temperature. So in our research, natural fiber is better than plastic, steel, and glass fiber to reduce temperature. That's all, Mr. Denny.
Thank you, Pak Agung. Sorry, I missed the question as well. So, Mr. Denny Bromo, is that answer the question?
Oh, yes. I mean, have you already compared between the modeling with the thermal conductivity test?
For experimental experimental test, not yet, but the next.
Okay.
Just predict. Okay, thank you, Mr. Denny.
Yeah, thank you, Pak Agung.
Thank you.
Because the time is limited, but I have one question for Ms. Debbie and also Mr. Heru Suryanto. Ms. Debbie, it's a very nice presentation on exudate, especially on resin from Rasak, and I forgot the other one, Leifis, if I'm not mistaken.
Bansirai.
Yeah. Did you also did an analysis on the in vitro level? Like, for example, if you're, for the anti-cancer, for example, or the other one for antibacterial, for example?
Maybe the next research.
The next.
Yeah.
Yeah. I would like to share that it will be nice if we can actually did that. Since in BRIN we have so many research center that actually can do the in vivo and in vitro test, so it will be good for that. And for Mr. Heru Suryanto, the epoxy composite, sir. If I may know, what is the best application if we make this epoxy from sisal or sansevieria? So with the properties that you examine, with the result that you have, do you think what will be the good application for this epoxy composite?
Okay, thank you, Ms. Dini. In our research, I do potency of sansevieria for reinforcement composite. Based on our data, 10% is higher interfacial shear stress. For the application, I think it is better for just structure.
For the structure,
Just structure, okay. But we don't test for macro composite. Just micro.
Yeah.
Thank you.
Okay. All right. Thank you, Mr. Heru, and thank you also, Ms. Debbie. We can discuss later. So now let's make a round of applause for everybody in the present that in session 1. Thank you very much for all good presentation. And now we are moving into the next session, session 2. So I would like to invite Dr. Vicky to play the short bio for the second session. All right, the first presenter in the second session is Ismadi. Mr. Ismadi is a young researcher at Research Center of Biomass and Bioproducts BRIN, completed studies at the Department of Mechanical Engineering, University of Gadjah Mada, and pursue a master degree at Department of Metallurgy and Materials, University of Indonesia. He is very enthusiastic in the field of biocomposite, natural fiber, and material process technology. The second one is Ms. Wafik Faradila Hasana. She graduated from the Bachelor of Civil Engineering Program Faculty of Civil Engineering and Planning, Trisakti University. Wafik's current research are mainly on the duration of hydrothermal carbonization and concrete properties. Professor Subiakto is a research professor at Research Center for Biomass and Bioproducts BRIN. He received his doctoral degree in agricultural science at Kyoto University, Japan. His research interests include the development of biocomposite from wood and natural fibers and their properties enhancement. The next presenter is Ms. Erlina Nurul Aini. Nurul Aini is an assistant researcher at the Research Center for Biomass and Bioproducts BRIN. She graduated from Forestry Faculty, Gadjah Mada University. Erlina's current research are mainly on the biocomposite field. The next presenter is Harmian Shah, STMT. He is a lecturer at Institute Technology Sumatra of Biosystem Engineering Department. He graduated master program from IPB University. Harmiansa. Current research are mainly on bioplastic from cassava starch and different types of cellulose. The last presenter is for the second session, is Miss Nidya Chitraningrum. Dr. Nidya Chitraningrum is a researcher in Research Center for Biomass and Bioproduct, BRIN, since 2021. She received a Bachelor of Science from Department of Physics, University of Indonesia, and Master of Science from Department of Electrophysics, National Chiayi University, Taiwan. She received her PhD in photonics from National Cheng Kung University in 2018. Her research interests span both materials physics and optoelectronics devices. Much of her work has been improving the understanding, material characteristic, and magnetic electrical performance of polymer or organic material for several advanced electronic devices, including solar cells, field effect transistor, or light-emitting diodes. Recently, she explored the development of activated carbon from several biomass resources for the electromagnetic absorber application. Thank you, Dr. Vicky. Can you please play the video of the five presenters, please?
Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Muhammad Rashidurido. I will present the result of our research entitled Isolation and Characterization of Lignin from Black Liquor of areca nut leaf seed with hydrochloric acid and phosphoric acid.
The background of this research is the area of areca nut plantation in Indonesia, approximately 147,000 hectares. From the areca nut plantation, its product waste that has not been utilized by farmers, one of which is the areca leaf seed, as much as 43,000 tons per year, usually just thrown away and burned. The lignin content in biomass varies depending on the type of plant. For areca nut, the lignin content is 19.59%. One way to extract lignin from biomass is the lignification process. Sample were pulped with active alkaline or AA and sulfidity. The delignification process product black liquor and pulp. Then the lignin is isolated from black liquor by adding acid, which can be organic acid or inorganic acid, and then obtain lignin powder. To the best of our knowledge, there is not a report about lignin isolation from craft black liquor of areca leaf seed. This study aims to examine the properties of lignin from black liquor product by pulping areca leaf seed using the craft method at different active.
The influence of hydrothermal carbonization duration and concrete properties.
Okay, we are very sorry. I think there's a mistake. Meanwhile, we are looking for Mr. Ismaidi video.
Okay, sorry. I think we can next to the next video.
Okay, for now we will play the next video first. We are very sorry, Mr. Ismaidi. We will make this right. Okay, please play the next video first.
The influence of hydrothermal carbonization duration and concrete properties. Natural fibers such as bamboo, jute, sisal, coconut fiber, and others are easily biodegradable and are recognized an alternative to synthetic materials such as glass and carbon due to their low cost, lightweight, unlimited availability, renewability, high elongation modulus, and strength. As a result, researchers and scientists exploit
natural fibers, and composite to produce environmentally friendly materials. By functioning as a reinforcing material, biochar has the potential to increase the mechanical performance of cement's composite. Fine biochar particles can contribute a filler effect and internal curing, which might also enhance the water tightness of cementitious material by densification and pore blocking action. Hydrothermal carbonization, or HTC, a novel type of biochar production process, has gained considerable interest from scientists in recent years. HTC can be used for biomass material with a lot of water in them. Coconut fiber, due to its availability and fibrous nature, could be a possibility for application as a raw material in bioadmixture. Low temperance HTC are appealing because of their simplicity, low contraction material cost, need for quick implementation with no material deterioration, and chemical-free nature. Chemical treatment has two advantages. The first one is improved surface morphology and lower non-cellulose fiber content. By waking hydrogen bonding, alkaline treatment, or NaOH, enhance fiber surface roughness. The purpose of this research is to evaluate the hydrothermal carbonization duration on the properties of concrete. In this study, we have two types of coconut fiber. The first one is untreated with the code BA and 234 is HTC duration, and the second one is pre-treated coconut fiber with code BAT. In this study, the cementitious material being used are Portland cement composite, fine aggregate, coarse aggregate, water, superplasticizer, and hydrochars. First, soak coconut fiber in 5% NaOH for 24 hours before ATC process. After that, the coconut fiber produced at 160 degrees Celsius for 2, 3, and 4 hours using the digester. After that, the mortar components were blended in a mixer. After we blended, we do a slump test and then put the fresh concrete into cylinder specimen and cured the concrete for 28 days. After 28 days, we can do the compressive strength test and splitting tensile test. The result is, in figure 1, illustrated the relation between ATC duration and value of slump. Figure 1 illustrates that the slump test results showed that concrete with pre-treated hydrochar performed better than concrete with untreated hydrochar. The slump of concrete with untreated hydrochar and pre-treated hydrochar increased with increasing ATC duration. Next is figure 3. Figure 3 is the correlation among slump and dry densities. When the slump rises, we could observe a small decrease in dry densities. This happened in two different types of concrete. As a result, the slump had no impact on the dry densities. Furthermore, it indicates that the dry densities of concrete with untreated hydrochar and pre-treated hydrochar are uniform for each ATC duration. In figure 4 shows that the ATC duration raised the compressive strength of the concrete with untreated hydrochar. However, the maximum compressive strength of concrete with pre-treated hydrochar was achieved at 2-hour ATC. At the 4 hours of ATC, the compressive strength of concrete with untreated hydrochar was quite greater in the A4 specimen. The ATC duration appears to enhance the compressive strength of concrete with untreated hydrochars while reducing the compressive strength of concrete with pre-treated hydrochars. As demonstrated by figure 5, there is an increase in compressive strength with rising of slump value for concrete with untreated hydrochars, but a reduction in strength with increasing slump for concrete with pre-treated hydrochar. The compressive strength was determined at highest slump in concrete with untreated hydrochars, when the slump in concrete pre-treated hydrochar was lowest. The compressive strength was the biggest. Figure 6 represents the correlation between dry densities and compressive strength. The greater the dry density of concrete with pre-treated hydrochar, the lower the compressive strength. This happened because the concrete's air pores were not filled by hydrochar. Furthermore, since the slump of concrete with pre-treated hydrochar was higher than 200 mm, it is probable that the water was trapped in the air voids in the concrete and didn't entirely evaporate. This is proved by the higher dry density of concrete with pre-treated hydrochar increase. Figure 7 illustrates the influence ATC duration on the splitting tensile strength. The longest ATC duration results in the maximum splitting tensile strength in concrete with pre-treated hydrochar. On contrary, the shortest ATC duration results in the highest splitting tensile strength in concrete with untreated hydrochar. The last one is figure 8. Figure 8 shows the effect of compressive strength and splitting tensile strength. The compressive strength of concrete with untreated hydrochar decreases as the splitting tensile strength increases. On the other hand, the compressive strength of concrete with pre-treated hydrochar increases also with the splitting tensile strength. Conclusion is the chemical treatment of coconut fiber increases the splitting tensile strength and slump value without decreasing ATC duration, and the duration of ATC has little effect on the dry densities. On the other hand, the ATC duration has an influence of compressive strength and slump value. Thank you.
Okay, that was the presentation from Ms. Wafik. Can we now play Mr. Ismadi video, please?
Gentlemen, this is I'm going to present my results.
The video is not show up, but the sound is already running.
Sulfur polyester composite.
Dr. Dian. Okay. Please be patient, everybody. The organizing committee is still trying.
Gentlemen, in this session, I'm going to present my results about investigation of fiber loading on physical mechanical properties of moisturized sulfur polyester composite.
Yeah. Okay. Can we replay it again from the beginning, please?
Uses of natural fibers as reinforcement.
Apologies, Bu Dini.
Yes.
I think we still have a problem.
Okay.
Maybe we can continue to the next video first,
I
and
think
then
I agree. We can just continue until the fourth presenter, and then we can continue with Mr. Ismadi. Mr. Ismadi, my apologize. We will fix this for you. Please, Dr. Vicky.
Thank you, Bu Dini. We are very sorry, Dr. Ismadi.
Good afternoon, ladies and gentlemen. I am Subiakto from Research Center for Biomass and Bioproducts, BRIN. I would like to present our work with title of Properties of Molding Products from Sorghum Bagasse combined with alang-alang leaves, sengon wood or bamboo using citric acid sucrose. The contributors of this work are Subiakto, Eko Widodo, Triati, Naomi Hutauruk, Rabia Adawiyah, and Kenji Umemura. The outline of my presentation is as follows: introduction, research purpose, materials and methods, results and discussion, conclusion, and finally, acknowledgement. Introduction. Indonesia has huge potential of fibrous sources such as sorghum, alang-alang, sengon wood, bamboo, and others. When they are processed into products which are generated, we can use the waste for developing new products, for example, molding products. This product can be used for furniture, kitchen appliance, craft, and so on. Some researches have been done on the use of wood or sorghum bagasse and citric acid sucrose for molding products. Citric acid is a natural adhesive that has been applied for biocomposites, while addition of sucrose improves the properties of the composite. However, research on effect of combination of raw materials using citric acid sucrose on the molding products properties has not been done. Therefore, the purpose of this research is to develop molding products from sorghum bagasse combined with alang-alang leaves, sengon wood, or bamboo using citric acid sucrose, and to observe effect of combination of raw materials on the molding products properties. The molding samples were prepared according to the formulation as shown in Table 1. We prepared 3 types of samples. Type A, sorghum bagasse Keller variety and alang-alang. Type B, sorghum bagasse Super 1 variety and sengon wood. And type C, sorghum bagasse Super 1 variety and bamboo. The ratio of materials can be seen here. While the raw materials, citric acid and sucrose ratio is 8:1:1. We use pressing temperature of 180 and 200 degrees C and pressing time 10 minutes at pressure of 4 MPa. Preparation of the sample is as follows. Raw materials were mixed with citric acid sucrose in the form of powder, then put in the mold and hot press. Samples were obtained. After condition for 1 day, samples were tested for bending strength and cyclic boiling test. Result and discussion. Density. Density of molding products mostly reach the target density of 1 gram per cubic centimeter. The raw materials do not affect the density. However, pressing at 180 degrees C showed lower density compared to 200 degrees C. According to the previous research, at 200 degrees C, citric acid melted and could easily form linkages with lignocellulosic materials to obtain good bonding. Modulus of rupture. Sorghum Keller only saw the highest MOR compared to sorghum Super 1 or other combination of raw materials. MOR decreases with increasing portion of alang-alang, sengon, or bamboo. The higher hemicellulose content in sorghum bagasse may cause this result. It is shown here that temperature of 200 degrees C gave higher MOR compared to 180 degrees C. Other research shows that temperature of 200 degrees C is optimal for preparing sorghum citric acid sucrose molding. Modulus of elasticity. When comparing to MOR, a bit different results were obtained for MOE. Sorghum Super 1 resulted in higher MOE compared to Keller. MOE decreases with increasing portion of alang-alang or sengon wood. However, surprisingly, sorghum combined with bamboo at all ratios resulted in high MOE. This may due to the fact that original bamboo fiber has high MOE. Result of citric boiling test include thickness change and weight change of all samples pressed at 180 and 200 degrees C. The changes of samples pressed at 180 degree are higher compared to 200 degrees C. Due to the time limitation, result of samples pressed at 200 degrees C only are presented. This figure showed thickness change of samples. A is sorghum alang-alang, B is sorghum sengonwood, and C is sorghum bamboo at different axes. Generally, sorghum-only samples show the lowest thickness change. The thickness change increases with increasing of portion of alang-alang, sengonwood, or bamboo. When we compare the three raw materials, thickness change of sorghum alang-alang showed the lowest, followed by sorghum bamboo and sorghum sengonwood. This may due to the different component of raw materials. Sorghum sengonwood samples were broken at the first boiling. This indicates a very big bonding. This figure shows weight change of samples pressed at 200 degrees C. Similar trend with thickness change is observed. The weight change increases with increasing portion of alang-alang, sengonwood, or bamboo. Also, it is shown that weight change of sorghum alang-alang is mostly similar to sorghum bamboo. Result of FTIR shows peaks around 1,700 per centimeter attributed to CO stretching due to the carboxyl group and or the CO ester groups, and peak around 1,200 per centimeter assigned to the CO stretching vibration band of esters group. The appearance of ester groups indicates that the carboxyl groups of citric acid reacted with hydroxyl groups of raw materials and sucrose to form ester linkage that strengthen the bonding. Conclusion. Molding properties of sorghum bagasse with citric acid sucrose were decreasing when combined with alang-alang, sengonwood, or bamboo. The temperature of 200 degrees C gave higher bending and water resistance compared to 180 degrees C of the molding products. Based on FTIR analysis, the formation of ester linkage was found, which resulted in good bending properties and water resistance. Finally, I would like to acknowledge JICA GST for SATREP's program, the project for producing biomass energy and material through revegetation of alang-alang fields for financial support, and integrated laboratory of byproducts BRIN for the facilities. Thank you very much for your kind attention.
Okay, thank you. We will stop now and we will try to share video of Mr. Ismadi again. Miss Nisa will help me to do this. Please, Miss.
Can you hear the screen?
Yes, now the screen is good. Can you play it? Let's try.
Teman-teman, in this session I will present my research about investigation of fiber loading and physical mechanical properties of mercerized sisal fiber polyester composite. The uses of natural fibers as reinforcement for composite material is increased from year to year and recent. Natural fibers can substitute synthetic fibers in composite material. One of the natural fibers that has potential to be used is agave, sisalana, or sisal fiber. However, the bonding between the fiber surface and the matrix makes the mechanical strength of the composite material not maximized. To improve the bonding of the fiber surface with the matrix, it is necessary to modify the natural fibers. Alkali treatment on natural fibers is one of methods to improve fiber matrix interface. The research investigating the effect of mercerized special fiber content on the physical and mechanical properties of the composite. The material used in this study is sisal fiber obtained from Sukabumi, West Java, Indonesia. The sisal fiber was 6.5% temperature solution for 2 hours and then rinsed with clean water until natural and dried. Mercerized sisal fiber with a moisture content of about 10% is used to make composite. The composition of the fiber volume fraction used is 5, 10, and 15%. The matrix was unsaturated polyester Eucalypt 157 and methyl ethyl keton peroxide certain from PT Justus Kimia Raya. Mercerized sisal fiber mixed with the unsaturated polyester and hardener then pressing by manual for 2 hours, then cooling in room temperature for 2 days. After that, the sample was testing in physical and mechanical properties. We use STM-D 63A potential testing and STM-D 790 for flexural testing. The results for all composites are in the range of 0.8 and 1.02 gram per centimeter cubic. Water absorption of composites reinforced by mercerized sisal fibers are below 5%, which indicated that the composites may tend to be compact and structurally white. This water absorption of composites reinforced by mercerized sisal fiber are better than the rest of Attica et al. 2020. It is about more than 8%. And the thickness swelling and water absorption increase along the edges of the fiber volume fractions. Thickness swelling below 2% value which indicated the composite dimensions are very stable. The tensile strength of the composite reinforced by sisal fiber increases with the increase in the volume fraction of sisal fiber. The tensile strength of the untreated sisal fiber reinforced composites with fiber volume fractions of 5, 10, and 10% were 18.6 megapascal, 26.15 megapascal, and 53.78 megapascal, and the tensile modulus were 1.9 gigapascal, 1.92 gigapascal, and 3.04 gigapascal. The tensile strength of the mercerized sisal fiber reinforced composite with fiber volume fractions of 5, 10, and 15% were 40.90 megapascal, 45.34 megapascal, and 58.06 megapascal, and the tensile modulus were 2.76 gigapascal, 2.61 gigapascal, and 3.31 gigapascal. The highest tensile strength was achieved by 15% volume fraction of composite reinforced mercerized sisal fiber, and the lowest in the composite reinforced by 5% of volume fraction untreated sisal fiber. The tensile modulus above is higher than the result of Ramesa et al. and Ghazali et al. In 2017. On coconut fiber reinforced composite, it was 0.4 up to 0.8 gigapascal. Structural strength tends to increase with the addition of fiber volume fractions. A significant increase occurred in the mercerized sisal fiber reinforced composite, which was 3 times with the addition of fiber volume fractions of 10% from 15 megapascal to 65 megapascal, while the flexural strength of fiber reinforced composite with the treatment increased by 83% at the addition of 10% fiber volume fractions. This indicates that the alkali treatment succeeded in solving the impurities and increasing in the interfacial bond of the matrix fiber. The flexural modulus reinforced by fiber is below the value of the flexural modulus of net polyester. The fracture cross-section of the sisal fiber reinforced composite is shown in figure beside. It can be seen that at a low fiber volume fraction, the unsaturated polyester matrix appears to dominate. Composite fractures at low fiber volume fraction tend to be more elastic and at high fiber volume fraction look more brittle. In the fiber volume fraction of 15%, fast fiber reinforced composite with treatment or with alkali treatment, it is seen that there is a fiber pool phenomenon. This happens because there are several fiber components that are not completely with it, so that they have a less strong fiber matrix bond. For the summary, we can take out the density, water absorption, and thickness swelling of the sisal fiber reinforced composite increase with the increase in the fiber volume fraction. Alkali treatments on sisal fiber can reduce the value of water absorption and thickness swelling of the sisal fiber reinforced composite. The water absorption capacity of the untreated sisal fiber reinforced composite was 7.8 up to 13.50% and 1.9 to 4.7% in the sisal fiber reinforced composite with alkali treatment. Alkali treatment can improve the physical and mechanical characteristics of sisal fiber reinforced composite. The tensile strength and flexural strength of the composite increase with the addition of the fiber volume fraction. While the flexural strength of untreated sisal fiber reinforced composite increased by 83% at the addition of 10% fiber volume fraction. This indicates that the alkali treatment succeeded in dissolving the impurities and increasing the interfacial bond of the matrix fiber. With the increase in the fiber volume fraction, the fiber pull-out phenomenon increases. Thank you.
Thank you, Dr. Nisa, to help us with the presentation. And then the next slide, please. Video, Dr. Vicky.
Okay, thank you, Bu Dini.
Good afternoon to the moderator and other conference participants. My name is Erlina from the Research Center for Biomass and Bioproducts. Today, I will represent our team to deliver our research findings related to the utilization of expired urea formaldehyde with the addition of wood vinegar for plywood and particle board manufacturing. Formaldehyde glue, especially urea formaldehyde or UF, can be considered the most dominant glue used in the wood panel industry. About 90% of particle board industry and 38% of plywood, OSB, and MDF industry use UF as the primary glue. The demand of UF is predicted to grow annually, as shown by UF market value, which continuously rising started from 2016 to 2022. The high demand for UF is due to its several advantages, such as high reactivity, excellent bonding performance, and low price. However, UF has relatively short shelf life. The effectiveness of glue past its shelf life tends to be reduced, and the glue is likely has to be discarded. So, the bad procurement management of UF in wood panel industry may lead to a massive UF waste problem. One characteristic of expired UF is it has higher viscosity than ordinary UF. The high viscosity can cause glue spreading disruption, such as poor flow, transfer, penetration, or uneven glue spread that may lead to the lowering quality of wood-based panel. In this research, we use expired UF in combination with wood vinegar. Wood vinegar contains 80 to 90% of water that might decrease the glue viscosity, and it also contains phenol, furfuryl, and furan that might increase the glue bondability. The aim of this research was to investigate the bonding quality of expired UF with addition of wood vinegar on plywood and particle board products. The main materials used in this research were mangium wood veneers, rubber wood particle waste, expired UF, and wood vinegar from mixed wood. The preparation of a glue mixture was generally done by combining expired UF and wood vinegar at different amounts, started from 0% to 30%. The pH and solid content of each glue mixture were then evaluated. Due to our viscosity tester limitation, solid content measurement was also used to predict the glue viscosity changes. For plywood production, the 3-ply plywood was made using a glue spread of 170 grams per square meter. The plywood was firstly cold pressed for 10 minutes and then hot pressed for 10 minutes at 120 degrees Celsius. After 1 week of conditioning, all plywood properties were evaluated according to the Indonesian standard. In the fabrication of particle board with a target density of 0.7 gram per cubic centimeter or cc, a 10% of adhesive amount was used. The press temperature applied was 120 degrees Celsius for 10 minutes. The properties of particle board were evaluated according to the Indonesian standard after 1 week of conditioning. All the data were analyzed using one-way ANOVA, followed by the 2 key tests. The evaluation of glue characteristics showed that addition of wood vinegar tended to decrease the pH and solid content of a glue solution. The pH of glue solution reduced from around 6 to 4 following the addition of wood vinegar. The solid content decreased to around 36% from previously around 49%. The decrease in pH and solid content was reasonable because wood vinegar had relatively low pH and solid content. The result of plywood physical properties evaluation showed that the addition of wood vinegar didn't affect the density and moisture content. The density of all plywood in this research were around 0.56 gram per cubic centimeter, while the moisture content were around 8%. The shear strength value of plywood in dry condition was between 10 to 16 kg per square centimeter, while in wet condition it was around 7 to 14. The dry shear strength value of plywood in this research was notably below the shear strength mangium plywood bonded with a normal UF in other study. This result could portray that there is a reduction of bondability in the expired UF. Despite that, all plywood in this research was able to fulfill the requirement of dry shear strength in Indonesian standard. The effect of wood vinegar addition was found to significantly increase plywood shear strength. The addition of wood vinegar potentially reduced the viscosity of the glue, as could be as could be depicted from the solid content value. This could result in a better adhesive penetration into the wood substrate. The presence of a phenol compound in wood vinegar also might prompt the increase in shear strength. All plywood in this study was able to fulfill the requirement of formaldehyde emission in Indonesian standard. The addition of wood vinegar was able to significantly decrease the formaldehyde emission in plywood up to 88%. The decrease in formaldehyde emission was possibly caused by the subtraction of formaldehyde glue in the glue mixture, along with the addition of wood vinegar. Like the result on plywood, the addition of wood vinegar also didn't significantly affect particle board density and moisture content. The density of plywood in this research was around 0.72 gram per cc, while the moisture content was around 7%. The internal bond strength of particle board in this research was remarkably lower than the internal bond strength of rubber wood particle board bonded with normal UF in the other study. However, the internal bond strength and screw holding strength of particle board in this research were still able to fulfill the requirement of Indonesian standard. The addition of wood vinegar was able to enhance the internal bond strength and screw holding strength significantly. The internal bond strength and screw holding strength of particle board without wood vinegar addition was able to meet the type 13 standard, while the board with addition of wood vinegar was even able to meet the requirement of type 18 standard. Wood vinegar addition was also able to significantly increase the particle board bending properties. Particle board without addition of wood vinegar has a MOR value that able to meet the type 8 standard, while particle board with the addition of wood vinegar have MOR values that even able to meet the requirement of type 13 and type 18. Furthermore, only the board with addition of wood vinegar at 20 and 30% could fulfill the MOR requirement of Indonesian standard. The increase of mechanical properties in particle board might be due to the better glue spreading and phenolic compounds in the wood vinegar. The addition of wood vinegar was also reduced the formaldehyde emission in particle board. All particle board in this research was able to meet the requirements of type F2 in Indonesian standard. Several conclusions obtained from this research were the expired UF that hasn't been fully hardened was still able to provide acceptable bonding strength, even though it was lower than the normal UF. Adding wood vinegar into the expired UF could significantly increase the glue bonding strength and overall composite product properties. The 30% wood vinegar amount produced the optimum properties of plywood and particle board. These are the references that I use in this presentation. And this is the end of my presentation. Thank you very much for your attention.
First chance, I want to, the first chance, I want, my name is Harmi Ansah, you can call him Harmi. I'm from Institute Teknologi Sumatera, Biosystem Engineering Department. The first chance, I want to present about my research. The topic of research is mechanical and biodegradable properties of oil, palm empty fluid branch, fiber reinforced banana peel starch, or polyphenol alcohol hybrid biocomposite for packaging application. This research I will present in the second international conference of lignocellulose from BRIN. This is my outline, my presentation. The first is background, the secondly research methodology, the third results and discussion, the last is conclusion. Okay, the first is background. My background, my background of research is the use of plastic as a basic packaging material in everyday life can have a negative impact on the environment because it can increase carbon dioxide emission. Conventional plastics have properties that are difficult to degrade. So, with the global use of conventional plastics and the increasing trend every year, it is very difficult to control waste from plastics. Plastic can decompose completely within 100 until 500 years, so it can trigger environmental pollution. Indonesia's waste production is estimated to reach 67 million tons by the end of 2019, of which 15% is plastic waste. One solution to overcome the problem of carbon emission and control plastic waste is to switch to using plastics that are more easily biodegradable in nature, namely biocomposite, which have the constituent elements of a matrix and reinforcements from nature, resulting in biocomposite becoming easily biodegradable materials. Okay, banana peels is an agro-industrial waste that is widely available and very cheap. Banana peel was account for about 30% of the weight of the whole unripe fruit. Oil palm empty fruit ones are lignocellulosic waste that has not been used optimally. Cellulose, hemicellulose, and lignin are the largest component of OPEFB waste. OPEFB component that has the potential to be used in the manufacture of bioplastic is cellulose. Cellulose contained in OPEFB is around 37.50% to 38.76%, and fiber content is 72.67%. Okay, purpose of my research is analyze the mechanical properties, namely tensile strength and modulus of elasticity, and the analysis two biodegradable tests was carried out to determine the percentage of the degradation value of bioplastic. Okay, the second step is a research methodology. This is my material. The material is oil palm empty fruit bunch, and the next banana peel starch, aquades, and AOH, PVA, glycerols, and research of tools is baker glass, oven, humidity meter, magnetic stirrer, hot plate, thickness gauge, analytical balance, glass plate, vernier calipers, universal testing machine, or UTM. Okay, this is a process of research. The first is the extraction of cellulose fibers. The secondly, extraction of starch. And the third, preparation of bioplastic films. And then we have to testing film of bioplastic. Okay, the first step, this is research, is extraction of cellulose. Extraction of cellulose. Extraction of cellulose fibers. The OPEFB fibers extraction method uses a modified method from previous studies. OPEFB fibers is cut into size of approximately 0.5 until 1 centimeters and clean it using distilled water. Then dried 40 days of the oven OPEFB fibers. Alkalization begin with 2 grams of OPEFB fibers dissolved into 500 millimeters of distilled water and 25 grams of NaOH solution for 2 hours with a heating temperature of 100 degrees Celsius. The OPEFB fiber is then washed from cleaning using distilled water to natural pH. pH is 7 and then dried. Furthermore, the OPEFB fiber is mashed with a mixer machine. The fine OPEFB fiber is uniform in size using a 100 mesh sieve. And then the next is extraction of starch. The first step, extraction of starch, is clean the banana peel, then cut into small pieces. And then banana peels are mashed with a smoothing machine, then filtered. The resulting filtrate was then allowed to stand for 24 hours. The starch is dried, crushed, then sifted. Okay, the next step is preparation of bioplastic. We use 3 grams of PPA is heat until it dissolves in 100 milliliters of distilled water, and we added 3 grams of starch and 2 milliliters of glycerol, and then added APFB cellulose with percentage. The percentage is 2%. 4%, 6%, and 8%. And then we have to dry in the oven at 50 degrees Celsius for 16 hours. So we were mechanical property testing is this is testing, and then we were variable properties testing. We had to prepare a sample before test. The first one sample was dried using an oven at a temperature of 50 degrees Celsius and wait to a constant wake. The second, insert into the soil to a depth of 8 centimeters and wake the degraded mass for 5, 10, and 15 days. This is calculation. This is a biodegradable test sample, and then the sample is put into the soil. Okay, we move to result and discussion. This is film bioplastic. Based on figure, it can be seen that the biocomposite film are refers with OPEFB fibers with a mixed matrix of banana peel starch and PPA produced a brown biocomposite film, because there is a browning process from enzymatic polyphenol oxidation. The increase in the percentage of addition of OPEFB cellulose fibers result in darker biocomposite film. The color density of the biocomposite film was due to the lignin content in OPEFB cellulose fibers. Okay, this is we can get physical properties of bioplastic films. This is type of characteristic of the physical properties of biocomposite films. The third column is thickness, and the fourth column is weight, and the last density is the density of biocomposite films. We can see that this results of basic physical properties. Okay, the next, the result of mechanical properties. We can see of grape. 0% has a tensile strength of 2.81 MPa. 2% has a tensile strength of 3.03 MPa. 4% has a tensile strength of 3.11 MPa. 6% has a tensile strength of 3.13 MPa. 8% has a tensile strength of 3.56 MPa. The more cellulose, the higher the percentage of tensile strength, because cellulose has a crystalline structure and has a long polymer chain. This and we compare with SNE 718.6 2016 tensile strength of 24.7 until 202 MPa. So this is not not rise with compared. Okay. The next is we have the strength of mechanical properties. This is we can see about from graph. The result is no person has a strength value of 41.856%. 2% has a strength of 25.67%. 4% has a strength of 23.99%. 6% has a strength of 22.1%. 8% has a strength of 22%. The addition of solution can make bioplastic stronger and stiffer, so that strength is lower. And last, from mechanical properties, we get modulus of elasticity. The result is all persons has a modulus of elasticity of 8.2 MPa. 2% has a modulus of elasticity of 12.09 MPa. 4% has a modulus of elasticity of 12.95 MPa. 6% has a modulus of elasticity of 13.84 MPa. 80% has a modulus of elasticity of 16.06 MPa. The more cellulose, the higher than percentage of the modulus of elasticity. Okay, we have most result of biodegradable testing of biodegradable. Okay, we can see from the graph figure of pressure loss weight degradation of the plastic. The percentage of degradation tends to decrease along with the addition of OPEFB cellulose concentration. Bioplastic that are naturally degraded in the soil are caused by the presence of decomposing microorganisms, soil moisture, and soil content. So we have the conclusion from this result, from this research. The conclusion is, based on the result of the research, the percentage of degradation with the fastest treatment, which is a variation of 0%, has an average loss percentage 21.2% on day 3. Day 6, it is 36.3%, and on day 9 is 44.9%. In this study, from the data on the biodegradation of bioplastics, it can be analyzed that is not by the Indonesian National Standard or SNA.
Good afternoon, ladies and gentlemen. Today I would like to present our paper on preparation and characterization of porous carbon-based oil palm anti-freight bond as a candidate material for an electromagnetic wave absorber application. I am Nidia Cicraningrum from Research Center for Biomass and Bioproduct. National Research and Innovation Agency, and this paper is in collaboration with the Research Center for Telecommunication and Research Center for Advanced Material, and also with the Department of Agricultural Engineering, Brawijaya University. And my presentation will consist of a brief introduction about the electromagnetic wave, AM spectrum, and how to reduce the ME effect, and the material and method we use in this paper, and result and discussion, including the XRD result, the EM wave absorption properties, SEM image, EDAX analysis, and conclusion. And the electromagnetic wave is a wave which can travel through the vacuum of outer space and form when an electric field couples with a magnetic field. There are many electromagnetic wave sources around us, such as the laptops, cellular devices, home appliances, et al. And the electromagnetic wave is divided according to the operating frequency. For example, some of electronic and communication devices, such as TV, cell phone, Wi-Fi, and microwave, it operates at the radio frequency and microwave frequency range. It's about 1 billion gigahertz to 300 billion gigahertz. And the question is, the EM wave around us is dangerous. The electromagnetic wave interference is the degradation in the performance of a device due to the field making up the electromagnetic environment, and the electromagnetic radiation around us will give the ME effect. And what is this example of the ME effect? For example, it can cause a reset of computer and losing of important data, and also can cause the malfunctioning of light controlling system due to use of laptop by passenger, and also it can cause failure of pacemaker implemented in patient due to walkie-talkie used by somebody, and disturb TV or radio reception due to the operation of the washing machine, for example, in this figure. And the most important dangers, it can cause the biological hazard that can injure the human tissue to cancer risk. And how to reduce the ME effect is by applying the EM absorber material. The model for the EM absorber material is place the metal plate in the back of the absorber materials, or in the back of the absorber material, so the transmission wave are always negligible, as shown in this figure. And we measure the reflection loss. That means the measurement of the amount of the light reflected back toward the source. And the low reflection loss means the high absorption. And here is the experimental setup in our work. We use the one-port vector network analyzer with the waveguide operate at the X-band frequency range that is in the range of 8 GHz to 12 GHz. And it connects to the receiver, PC, or computer to see the S11 parameter of the reflection loss of a material. And the second is the dimension of the waveguide and the material we use. The material is put in here, and the back metal placed in the back. And the sample used in this work is the activated carbon that is prepared from the OPEFP material. And for the first step, we do the hydrothermal carbonization at 180 degrees Celsius for 8 hours to form the hydrochar based OPEFP, and we call it HTC OPEFP. And the second, we do the chemical activation using 20% KOH concentration, and then followed by the physical pyrolysis carbonization at 800 degrees Celsius for 2 hours under nitrogen atmosphere to form the activated carbon based OPEFP, and we call it AC20. Here is the XRD result for the raw OPEFP, STC, and for the activated carbon. Here you can see that for the raw material, there is a peak around 15 degree and 22 degree. This is correspond to the crystalline cellulose 1 structure. And after the hydrothermal carbonization, the peak, these two peaks, is become sharper because the hydrothermal carbonization will remove some amorphous component of the cellulose, such as hemicellulose, lignin, and amorphous cellulose. And after the activation and heat treatment, this peak will be removed because the activation and heat treatment will destroy the crystalline cellulose structure, and then it will characterized by the presence of a broad and weak diffraction peak about 15 to 22.5. This remove of these two peaks is because the intra and intermolecular hydrogen bond of cellulose or PFP crystalline structure is break under the physical carbonization process. And for the VNA of the raw OPAFP, STC, and activated carbon is shown in the figure. Here we can see from the table that the reflection loss from the activated carbon SC20 is increased by minus 32.21 decibel compared with the STC OPAFP only minus 4.3 decibel. And the microwave absorption efficiency was increased from 39.05% to 97%. And the transformation from the OPAFP into activated carbon can enhance the EM absorption properties in expand frequency range. We correlated this enhancement of the EM absorption properties due to the change of the interfacial structure. To identify the change of the interfacial structure, we perform the SEM measurement. Here is the SEM image of the hydrogen OPAFP and activated carbon OPAFP. Here you can see that for the hydrogen OPAFP, there is no pores observed. But for the activated carbon OPAFP, there are many pores observed. The pore structure of the material will provide multiple paths on the incident EM wave that can improve attenuation ability of EM wave. Therefore, enhance the interface polarization between EM wave and absorbable material to increase the absorption properties of the activated carbon. And here is the element analysis using the EDAX for the hydrogen and activated carbon. Here you could see the carbon element of the activated carbon is increased to 84.4% compared with the hydrogen OPAFP, but the oxygen element was decreased from 25.3 to 8.8%. The physical carbonization process with the absence of the oxygen will remove mostly of the oxygen element in hydrogen OPAFP, result in the maximum carbon element in activated carbon. And for the conclusion, we have successfully synthesized the activated carbon from the biomass of OPAFP using the hydrothermal and pyrolysis carbonization, also with the KOH activation. And the intra and intermolecular hydrogen bonds of cellulose OPAFP is break under the physical carbonization process, and EM wave absorption properties is increased to minus 32.12 decibel with the microwave absorption efficiency about 97.54%. And the biomass of OPAFP derived activated carbon offers some super purity due to its low cost raw material and processing, environmentally friendly and controllable EM wave absorption properties, making the OPAFP material become a potential EM wave absorbable material in the future. Thank you for attention.
Okay, that was the second session of this afternoon. A lot of interesting presentation. I would like to invite all of the presenters to turn on your camera, please. We have Dr. Harmiansa, Dr. Nidia, Dr. Erlina, Professor Subiakto, Dr. Wafik, and Dr. Ismaidi. Can you please turn on your camera, and everybody also, so we can have more interactive discussion? I would like to invite all other participants to question the presenter first, please. I have a raised hand from Dr. Nidia. Please, Dr. Nidia, to whom you would like to ask the question, and please.
Thank you, Mrs. Dini. I would like to ask to Wafik Faradila Hasana. In your paper, you provide a lot of sample condition in your result with condition, with best condition for is you recommend for the concrete properties in your data. Thank you.
Dr. Wafik, please to answer the question right away. Can you hear Dr. Nidia question before? Dr. Nidia, can you please repeat your question again? Because it seems Dr. Wafik has a trouble in...
Hello, Dr. Wafik, can you hear me? Hello?
You're still on mute, Dr. Wafik. Can you please unmute? Let's unmute.
Maybe I want to ask, which is the best condition of your sample, because you provide a lot of data with untreated and pre-treated and along a short and long time of treatment. Yeah, which is the best condition for the concrete properties.
Okay, the question was, what was the best condition among those various treatment? Can you please explain? We still cannot hear your answer. I think there's probably problem. Perhaps can you just type your answer? I'm sorry, Dr. Nidia, because time is limited. So maybe Dr. Wafik can just answer by typing the answer, and then the next question is, please, any raise hand? Please, Dr. Bernadetta, to ask the question.
Okay. Hello. Can you hear my voice?
Yes, clear.
Okay.
Thank you.
Okay, thank you. I have a question for Professor Subiakto. According the conclusion that sorghum bagasse with citric acid can decrease when combined with alang-alang and sengon or bamboo. Could you explain why this for this possibility, why this can be happen? And then next for Pak Ismadi, sorry. Okay, according to the Mr. Ismadi, that alkali treatment can improve the mechanical compared to the untreatment. Could you explain why this happened? And then for Miss Erlina, yeah, the title is very unique. I see that she using expired UF. My question is it okay for the emission, especially because it's expired UF? Have you checked it yet? And then what is the strong reason using expired UF? Okay.
Okay, thank you, Ms. Deta. I would like to please for Professor Subiakto to first answer the question from Deta.
Okay, thank you very much. Can you hear my voice?
Yes, clear, Professor.
Yeah, I'm sorry, I am not turned on my video because I'm in outside. Yeah.
No worries, Prof.
Thank you. Thank you very much for your question, Mbak Deta. Yeah, according to our data, that when we combine the sorghum with other materials, bamboo, sangon wood, or alang-alang leaf, and then the properties decreases. One of the possible cause of this one, I think, because of the chemical content of the raw material. Sorghum has a high hemicellulose content, and this is a very good when we bond it with citric acid and sucrose. but maybe the bamboo and other materials have a lower emissive content. That's why the bonding of the sorghum is better than other material. Thank you.
Okay, thank you for the answer, Professor. Is that enough, Ms. Deta?
Yeah.
Oh, thank you very much. And for the next, thank you, Prof. Subiakto. And for the next question for Dr. Ismadi, please. Dr. Ismadi to answer.
Okay, thank you. The effect of the alkali treatment on mycelial fibers is increasing the mechanical properties because the alkali treatment could dissolve the lignin and the other impurities that it can increase the surface bonding fiber and matrix. I think enough, Mrs. Deta.
Oh, okay. So the alkali treatment can give the functional group for the material like that, yeah, Mister?
Yes. Yes.
Okay. Thank you.
Thank you. And for the next question, please.
For Miss Erlina.
Yeah, Miss Erlina, please can you?
Okay, thank you. Thank you, Miss Deta, for the question. First, for the first question related to the formaldehyde emission, I had evaluated the formaldehyde emission of both plywood and particle board, and all plywood and particle board in our research was able to fulfill the formaldehyde emission standard, and the addition of wood vinegar was further decrease the formaldehyde emission of both products. And for the second question, why I use expired urea formaldehyde? Because as I had explained in the introduction section, the demand of UF in wood industry is actually quite high, and when the UF glue already past its shelf life or expired, usually it tend to not use anymore, and can cause a massive waste problem. So I want to utilize the expired UF to reduce the amount of glue waste in wood industry. That's all. Thank you.
Okay. Miss Dini?
Yes.
Can I give 2 questions more for Mr. Harmiansyah and Miss Nindya?
Okay, but the last question was, is that all right? Are you happy with the answer?
Okay.
Okay. Okay, so what the question for Mr. Harmiansyah and Dr. Nindya?
Okay, for Mr. Harmiansyah, I see that in your conclusion that the fastest degradable is invariant 0%, but the highest tensile is 8%. And my question is, according to you, which variation that has a good recommendation to both of the degradable and mechanical properties? And then for Ms. Nindya, could you explain about your statement that intra and intermolecular H bond, especially in the cellulose of OPEFB, is breakdown? Could you confirm using your characterization? Thank you, Miss.
Mr. Harmiansyah, please. Harmiansyah, please.
Thank you for your question. For me, I think my recommendation of various of cellulose for the highest mechanical and biodegradable is based on my research Ada gini. Wait. Okay. Based on my conclusion is I get the highest of mechanical properties is various 8% cellulose for tensile with value is 3.56 NPa. I think mechanical and biodegradable is very different various, but I think standard of SNE is standard SNE be like the parameter of for a standard mechanical and biodegradable. So this my conclusion. I think various, the best of various is 6% cellulose to get to good or highest value. I think like that. Thank you.
Thank you, Mr. Harmiansa. And Dr. Nidia, please.
Thank you for question, Mr. Bernadetta. For the explanation, maybe the cellulose is consists of the H bond to form the crystal structure of the cellulose, and after the pyrolysis, after the activation and pyrolysis of the cellulose, the bond is changed to form more amorphous. Therefore, we can see from the XRD there is no peak at the 10 and 20. So we conclude that the hydrogen bond is break under pyrolysis. Yeah, that's my answer.
Okay, thank you, Miss.
Thank you, Dr. Nidia, and also Dr. Bernadetta to ask the question. I think we can wrap up the second session in this afternoon. Are we going to move to the next session? No break, right? Dr. Vicky, can we continue to the third session? Before that,
yes.
Have a round of applause for the presenter on the second session. Thank you very much. All are very interested, and I hope we can make more collaboration in the future. So the third session, I would like to welcome Dr. Vicky to play the short bio for the third session.
Okay, thank you, Budini.
3 more presenters, is that correct? Yeah.
Yes, we have 3 more presenters.
Please be patient, everyone. We still have 3 more interesting talk. The first one will be from Dr. Ismail. Dr. Ismail Budiman is a researcher at Research Center for Biomass and Bioproducts BRIN. He graduated from Forest Products Science and Technology Study Program IPB University. And his current research are mainly on biocarbon, biocomposite-based carbon, and cement carbon composites. The next presenter is Dr. Ria Yolanda Arundina. Is graduated from Brawijaya University. He is currently a postgraduate student in chemical engineering at University of Indonesia. She works as research assistant at Research Center for Biomass and Bioproduct BRIN, with the research topic are mainly on biomass-derived carbon for functional materials. And our last presenter, but not the least, is Dr. Lisna Evianti, born and raised in Menes, Pandeglang, Banten. Lisna graduated with bachelor's and master degree from Gajah Mada University. She is now studying at IPB University in Natural Research Management and Environmental Science. She started working as a researcher at the Microbiology Laboratory of Forest Research and Development Center in 2011-2014, and then joined the Chemical Laboratory of Forest Product Research and Development Center from 2015-2022. She is now currently working at the Research Center for Biomass and Bioproducts BRIN, and her research focus are the research on chemical energy, non-timber forest product, especially biocarbon and catalyst material. The works were published in several papers related to these topics. She tends to enjoy life in simple way as well as for her career. She is extrovert and cheerful personality are part of her. We can see that from her picture, yeah. But sometimes she's overthinking too. Okay, thank you, Dr. Lisna. Now, can we please play the video from the three presenter, Dr. Vicky? Thank you.
Good afternoon, everyone. My name is Ismail Budiman, and I'm from Research Center for Biomass and Bioproduct BRIN. This opportunity, I would like to present our research, and the title is Activated Charcoal from Robusta Coffee Waste as Absorbent of Pollutants, Absorption Kinetic of Iron to Chloride. Let's start with the introduction. As we know that one of the problems of industrial waste is heavy metal. It must be a concern of various parties such as the government and also the industry. One of the heavy metal wastes that have an impact on human health is iron metal. The material that can handle this pollutant is activated charcoal. The charcoal can absorb heavy metal well because it has pores and a large enough of surface area. One of the activated charcoal that can absorb metal ions is activated charcoal from Robusta coffee waste. Based on the background, this research objectives are as follows. The first one, to know the effect of treatment of silica to activated charcoal from Robusta coffee waste material on the properties, the surface area, and the pore size of activated charcoal that has been produced. And the second one, to determine the absorption ability of activated charcoal against iron to chloride using activated charcoal from Robusta coffee waste. These are the materials and methods. For materials, we use Robusta coffee waste, silica gel, sulfuric acid, hydrofluoric acid, ethanol, potash, iron to chloride, and methylene. While the equipment used include a rotary digester, FTIR, TAAS, and FSM DX. These are the research methods. Starting from the preparation of materials, we proceed to add silica to the pore composition. It is followed by hydrothermal carbonization at a temperature of 150 degrees Celsius for 6 hours and activation at a temperature of 600 degrees Celsius for 15 minutes. Furthermore, activated charcoal obtained was characterized to determine the properties of the charcoal, functional group, and also morphology and dimension size. The last step is to see the ability of charcoal to absorb iron to chloride. This slide is an illustration of the process of making activated charcoal. Start with the dehydration of Robusta coffee waste until the leaching activated charcoal, leaching silica of activated charcoal with hydrofluoric acid. This is the research and discussion. The following is an appearance of activated charcoal from various silica addition treatment. And it is a graph of the research of FTIR analysis of coffee waste, its hydrochar and activated charcoal at various levels of silica addition. This slide on the left shows CH bonds in coffee waste and OH bonds in hydrochar. It shows that this activated charcoal material has alcohol and carboxylic acid groups that can be used as absorber from materials in the form of solution or gases. Well, on the right side, we can see that In header chart, the wave number of 1055 per centimeter and 789 per centimeter indicates the COC asymmetric strain functional group due to the addition of silica treatment. On this slide, in the FTIR analysis of activated charcoal, we can see at the wave number of 1068 to 1178 per centimeter, that there is a CO bond, which indicates that there is still elemental oxygen that is not decomposed and is bound to carbon. Well, at that number between 450 to 800 per centimeters, there are COC bonds as a result of the addition of silica. The following is the morphology of the copious activated charcoal in various silica treatment using 8%. And meanwhile, this is the results of the analysis using EGX on the elemental forming charcoal from coffee waste. The results of the analysis of using EGX can be seen that the element of carbon, oxygen, and silicon are the main elements contained in activated charcoal. This is the result of characterization using DET to see the dimension of activated charcoal. Based on the pore size, we can classify the activated charcoal into mesopores and macropores, with size between 2 to 100 nanometers. From the characterization results, we can also see that silica treatment can increase the surface area of the activated charcoal. It is the activated charcoal properties based on Indonesian National Standard. We can see that silica treatment can improve the properties of activated charcoal in almost all parameters because it is related to the increased surface area of activated charcoal due to silica treatment. For activated charcoal, silica treatment with a ratio of 1:1 or A1 count and 2:1 or A2 count almost all met the standards except for methylene blue. It happened because the value of methylene blue is influenced by the surface area and pores, and also the chemical properties of the activated charcoal. Here is the ability of activated charcoal to absorb the metal pollutant iron 3 chloride. You can see that the absorption effectiveness of activated charcoal without silica is greater than that of activated charcoal with silica. Then the effectiveness of its absorption will also decrease as the silica content decreases. It is also related to the pore size, where the larger the pore size, the lower the absorption efficiency. This is the flow of water before and after contact with activated charcoal in various silica treatment. We can see that the water will be clearer after contact with activated charcoal in various types of silica treatment. These are the conclusion. The first is the adding silica effect, the charcoal properties, force dimension, and absorption efficiency of activated charcoal on iron 3 chloride ions. The second one is that the larger the resulting form reduce the effectiveness of activated charcoal absorption on iron 3 chloride ion. That's all of my presentation. Thank you for your attention.
Malin Sultan and Mrs. Resti Marlina. Introduction. Oil palm cells are one of the biomass that contain high lignocellulose. Oil palm cell has become a promising raw material of activated carbon. The synthesis of activated carbon produced from biomass passed through the carbonization and activation process. There are two carbonization methods, which are hydrothermal or wet method and pyrolysis or dry method. The activation process consists of chemical, physical, and a combination of the two methods. Combining the chemical and physical method can produce a higher surface area and absorption capacity. Activated carbon is porous solid which contains 85 until 95% carbon. Material activated carbon has a broad range of applications such as water purification, gas filter, energy storage, and absorbent. Implementing activated carbon for wastewater treatment has been an important issue in order to realize zero waste and clean technology. This research was conducted to determine the characterization of activated carbon from biomass waste by adding phosphoric acid and zinc chloride activators to produce the activated carbon with a high specific area. Proximate analysis, including moisture content, ash content, polarimeter, and fixed carbon, was carried out to determine the characteristics of activated carbon compared to technical activated carbon standard in Indonesia. Furthermore, the material characterization was also observed using Raman, XRD, and nitrogen absorption desorption. The absorption capability of this material was conducted using methylene blue and rhodamine B tests. Methods and procedure. Retreatment. Raw UPS reduce the size using ring flaker and sieve pass through 20 mesh and retain at 10 mesh. After that, the UPS sample was using water and drying with oven at 105 degrees Celsius for 24 hours. We got UPS sample. UPS sample was going through the hydrothermal carbonization at 220 degrees Celsius for 8 hours. After that, after going hydrothermal carbonization, the UPS sample called hydrocharge. Hydrocharge drying with oven at 105 degrees Celsius for 20 hours and after that, grinding and sieving. Sieving past through 100 mesh, we have hydrocharge powder. Activation process. The activation process was performed through two processes, which are chemical activation and physical activation. Hydrocharge was chemically activated by stirring it for 2 hours in 20% weight per weight phosphoric acid or zinc chloride solution. After that, dried in oven for 3 until 6 hours at 115 degrees Celsius. The physical activation was carried through pyrolysis process in furnace at 800 degrees Celsius for 1 hour. The sample that had been activated with phosphoric acid and zinc chloride was washed with deionization water. After the washing process, the sample is called activated carbon. Several analysis and characterization were conducted for the activated carbon sample, including proximate analysis, Raman, XRD, and nitrogen absorption desorption. Analysis. Proximate analysis was performed to define the moisture content, ash content, polarimeter, and fixed carbon according to SNE standard of technical activated charcoal. Based on the data shown in the table, moisture content, ash content, polarimeter, and fixed carbon of sample with activator have met the standard of SNE. The high yield of activated carbon caused high ash content and polarimeter from activated carbon, so the fixed carbon produced is lower but sufficient to meet SNE standard. The use of activators can prevent ash on activated carbon compared to activated carbon without chemical activation. As non-activated has the highest ash content and does not meet SNE standard. Raman spectroscopy. Raman spectroscopy analysis is generally used on detecting various forms of carbon such as diamond, graphite, and amorphous. two main peaks are used to detect the structure formed on carbon, which are the D band and G bands. The D band represents the disturbance or irregularity. The G band represents the graphite peak, which has a stable structure. The ratio of the intensity of the D band and G band formed in its spectrum indicates the degree of irregularity of the carbon structure. The Raman spectrum for amorphous carbon consists of two peaks, which are the D and G band. Based on the Raman spectra of the activated carbon, the D and G band sample have shown an amorphous structure carbon. The ratio of D band and G band value is close to 1, indicating that the activated carbon degree of carbonization is good, where the irregular structure is quite balanced with the graphite structure. XRD. From the XRD result, we know that in the hydrothermal process, there is a change from type 1 polymorph cellulose to the type 2 polymorph cellulose. From all the samples, we found a more porous peak around the angle of 2 theta 22 degree and 44 degree. On activated carbon phosphoric acid was found crystal peak of activator phosphoric acid, and on activated carbon zinc chloride were found crystal peak of the activator zinc chloride. The discovery of phosphoric acid and zinc chloride indicates that the washing process is still not perfect and required the neutralization process to remove the presence of activators. Meanwhile, in Asia non-activated, samples are only porous carbon peak were found. Nitrogen absorption and desorption test. From the test, we have isotherm curve and pore distribution. Based on the table, it can be seen clearly that the result of Asia non-activated have the lowest result among other samples. This proves that chemical activation expands the surface area and increases pore volume. From the curve, the Asia non-activated isotherm curve that is formed is close to type 4, which shows a mesopore structure, with the hysteresis curve type H2, which identifies the combination of micropore and mesopores with mesopore domination. The activated carbon phosphoric acid and activated carbon zinc chloride isotherm curve that are formed are close to the type 1, which show a micropore structure, but hysteresis is still found on the curve, indicating that the pores are widening. The type of hysteresis curve for the activated carbon phosphoric acid and activated carbon zinc chloride samples show the type of hysteresis curve H4, which identifies micro-mesopores carbon. Pores dominated by micropores, and when viewed from the pores arrangement, activated carbon of zinc chloride is more irregular when compared to activated carbon of phosphoric acid.
Dr. Vicky, are we having problem with the video?
Yes, Bu Dini.
Able to reduce the concentration of methylene and rhodamine B. From the test result, which were clearer than the initial solution.
Seems like we are having problems.
Yes. Yes, Bu Dini, I think it's the video, not the...
Oh, the video, not the...
Yeah, not the signal. Yes. And then it's continue.
This to produce high-yield activated carbon from OPS using hydrothermal and pyrolysis methods that have met SNE standard of technical activated charcoal. From Raman spectroscopy for activated carbon sample shows an amorphous carbon structure and was supported with XRD result of activated carbon. The peak detected at 22 degree and 44 degree of 2 theta. The highest surface area of the sample was activated carbon of phosphoric acid. From the PSM result of activated carbon show that the activated carbon has formed mesopores and micropores, which indicates that activated carbon has promising porosity. The absorption capacity test showed that activated carbon was able to decrease the concentration of methylene blue and rhodamine B. In the activated carbon structure still can be found the impurities from the activated agent. The impurities decrease the performance of activated carbon in purifying wastewater. Therefore, the neutralization and washing process need to be carried out to remove the impurities and increase the absorption performance of activated carbon. That's all for my presentation. Thank you very much for your attention.
Assalamualaikum warahmatullahi wabarakatuh. Thank you for the opportunity for us to participate in this conference. My name is Lisna Evianti from the Research Center for Biomass and Bioproduct. On behalf of our team, I will give a presentation briefly about our research. The title of this research is Nickel-Impregnated Activated Carbon Properties from Mixed Wood Waste and its Application for Hydrocracking Reaction of CMANG. Okay, the wood processing industry produces byproducts from flax and powder waste, which are generally not appropriately utilized and increase pollution. The production of wood waste provides an opportunity to process wood into other valuable material. Several bioproducts from wood and wood waste are obtained through pyrolysis reaction, including wood vinegar, energy, and biocarbon. The biocarbon modification was conducted based on application purposes. One of the biocarbon modification is impregnating metal to work optimally as a material, for example, for catalyst material. Many reaction processes require the assistance of catalysts, including esterification, trans-esterification, cracking, hydrocracking, hydrogenation, catalytic reaction, and secondary metabolic production. Several metals such as nickel, chrome, gold, and other metals impregnated in activated carbon for pyrolysis or cracking of several oil. And resulting from that, the use of activated carbon could increase the content of aliphatic, aromatic, phenolic compounds, and selective for benzene products. From these studies, the results about nickel-impregnated biocarbon from wood waste was conducted to determine the product's properties. This is our methods. The first one is nickel-impregnated biocarbon synthesis. Mixed wood waste is cleaned and heated in pyrolysis reactor for carbonization process, and then the carbon is activated using acid and followed by heating process into activated biocarbon. And then the activated biocarbon is impregnated with nickel metal using reflux, and then followed by calcium with microwave assist. And this is properties analysis of nickel-impregnated biocarbon. The first is proximate analysis and the number of biocarbon based on Indonesian national standard and acidity of biocarbon using the base adsorption method of ammonia and pyridine, X-ray diffraction to determine the degree of crystallinity of the sample, and surface area analyzer to calculate the surface area total for volume and the average pore radius. And the last is FTIF to determine the functional groups of biocarbon material. This is for the hydrocracking process. There are 3 steps for hydrocracking process reaction. The first one is reactant preparation, hydrocracking process, and biofuel products analysis. Manganese oil prepared by hose press hydraulic method and filtered to remove impurities, And the hydrocracking reaction was conducted using a reactor with hydrogen addition. And for the ratio, catalyst and feedstock are 1 to 100. And the reaction temperature and time is 2.5 hours reaction time. And for biofuel products, we collected and analyzed using GCMS to determine the selectivity product. This is our result. The first one is biocarbon proximate analysis. From this figure, we could see that the activation and impregnation of the biocarbon lead the increasing of fixed carbon, and the moisture, ash, and volatile matter content generally follow the SNE requirements, and the metal impregnation process also increase the ash content, and the heating process of impregnation method leading to the increasing ash and volatile matter forming and calculated fixed carbon decrease. And this is for the biocarbon adsorption activity. From the table, we could see that the activation and impregnated biocarbon lead the chance of the adsorption activity. For iodine number, chloroform, benzene, pyridine, and ammonia adsorption tend to increase after activation and impregnation process. And local performance of biocarbon due to impurities that partially cover the pores, and the activation and calcination process increase the iodine number due to opening of pores and removing impurities. And this is for the biocarbon functional group. From this figure, we could see that there are several functional groups in the sample. There are OH, CH, OH, and CC group in the sample. For biocarbon crystallinity and morphology, the sample calculation showed that the crystallinity of biocarbon, activated biocarbon, and nickel impregnated biocarbon was 30.30%, 52.63%, and 52.33% respectively. And the presence of Ne metal showed at 2 theta of 44, 52, and 77. And from the same image, we could see that the activation process highly obtains the open pore due to the impurity removal. And for the surface area analysis of biocarbon, from the table, we could see that the activation and Ne impregnation biocarbon lead the increasing of surface area. And the surface area is one of the crucial parameters in the determining porosolid quality, illustrate the number of active sites on the catalyst surface that leads to its catalytic activity. And this is for the distribution and selectivity products of Chemangha's hydrocracking reaction. From this figure, we could see that the most significant composition produced by the conversion of Chemangha's oil using nickel impregnated biocarbon is a group of aliphatic hydrocarbon, more than 40%, carboxylic acid, alcohol, ketones, and ester compounds. The three main components of the hydrocracking products are lauric acid, decan, and tetradecanol. And the formation of the aliphatic hydrocarbon group indicates that the hydrocracking process has been running efficiently. This hydrocracking process does not produce unwanted compounds such as furan and polycyclic aromatic hydrocarbon. This is our conclusion. The properties of Ne impregnated carbon from proximate analysis. The yield, moisture, ash, volatile, and fixed carbon were 39.20%, 6.5%, 7.30%, 30.67%, and 62% respectively. The nickel impregnated bicarbon adsorption to iodine, pyridine, and ammonia were 1700 meter quadrat per gram, 2.8 millimole per gram, and 8.8 millimole per gram respectively. According to the FTIR analysis, there was a reduction in the OH functional group and lignin structure, forming a carbon aromatic during the carbonization process. And the surface morphology of biocarbon changed after treatment with the formation of pores. For the surface area, increase after activation and impregnation. They applied any impregnated biocarbon into Chemalha's hydrocracking resulted in aliphatic hydrocarbon, mainly containing dodecane as a valuable and desirable product. For this reason, and in impregnated biocarbon prospecting to develop as bioproduct green technology as a catalyst for biomass conversion. This research was partially supported by the Ministry of Environment and Forestry, and we would like to give our warm thanks to our colleague in Chemistry Integrated Laboratory of the Center for Standardization of Sustainable Forest Management Instrument. Thank you for your attention.
Thank you very much. I guess that's all from the three presenters in our last session. We have Dr. Ismail Budiman, and then Dr. Ria Yolanda, and Dr. Lisna Evianti. I would like to invite you to open your camera, to turn on your camera, so we can have an interactive discussion also with other participants here. I would like to invite some questions for them, please. Is there anybody who would like to raise the hands or directly ask the presenter? It seems that our last presenters, all of them talking about carbon, which is very important at the moment because it's an advanced materials, and Indonesia, I guess, has some very good potential to develop this product, especially because we have a lot of biomass. Again, I would like to invite if there's any question from the participant. Dr. Deta, do you have any question? Yes, please.
Okay, thank you, Dr. Dini. My voice is clear?
Yes, clear. Thank you.
Okay. I have a question. Presenter for Mr. Ismail Budiman. In your you mentioned that in activated cycle.
I guess your voice is
yes.
Yeah. Yeah.
Okay.
Can you repeat it, please?
Okay. Okay. I'm repeat. For Mr. Ismail. Okay. In your presentation, you explained that silica in activated charcoal from coffee affected to absorb iron. Could you explain the mechanism why the silica could very affected to absorb the iron? And then for Ria, Miss Ria, from the conclusion, you mentioned that AC, activated carbon, was able to decrease the dye that methylene blue and rhodamine B, isn't it? And then, but when I see from the value, it's not really significant compared with the non-activated carbon. So, according to you, could you explain what is the mechanism of the of your sample? Why is absorption of the rhodamine B and MB it's not give the significant value? Maybe from the mechanism, if I can see the pore, the surface, because you explain from the BET characterization. And then for Miss Lisna, it's very new for me to.
Miss Deta, your voice is gone. Can you repeat for Miss Lisna, please?
Okay. Hello?
Yeah, okay, now it's up.
Okay. Hello. For Miss Lina, I want to know about the calcination process.
I think it's
mentioned-
down again, sorry.
Kenapa ya?
Yeah, okay, coba
Wait.
lagi. Try again, please.
How? It's clear?
Yeah.
Kelihatannya sinyal saya. Okay. For Miss Lina, could you explain
It seems down again. Maybe you can write down the question. Okay, please, Miss Dr. Ismail, to answer the first question from Dr. Deta.
Okay.
Dr. Deta, for Miss Lisna, please type the question. Thank you.
Okay, thank you very much, Dr. Dini, for opportunity. Thank you very much for this data for question. Okay, how about the mechanism silica in activated charcoal can absorb the iron 3 chloride ion? Okay, in the study, in the study and in the previous study, this silica treatment is acting as a template of the activated charcoal, and she acts as the to improve the surface area and also pores of the activated charcoal, and also the silica can construct the binding site for catch the positive ions, and iron have the 3 positive ions, and the silica can construct the binding sites to catch the ion of iron chloride. That's my answer.
Oh, okay. Thank you, Mr. So it means that the electron between in the Se and the O, right?
Yes.
Okay.
Exactly.
Okay, thank you.
Thank you.
It's quite difficult. What is that, science? Yeah, the science behind it. Okay. What about the next question for Dr. Ria Yolanda? Can you please answer the question?
Okay, for methylene blue and rhodamin B is mesopore in size, but in my activated carbon in my research is mostly micropore. So from the data we saw not significantly have difference because methylene blue and rhodamin B is mostly in mesopore. Does that answer the question?
Was that answer the question, Miss Deta? Maybe we can discuss next in the
Discuss next.
Yeah. Okay.
Okay. Oh yeah.
Dr. Lisna, can you
Yeah.
repeat?
Okay, I will repeat. Yeah. For Dr. Lisna, I want to ask about your calcination process. You say that the calcination process using the microwave assistant could prevent the agglomeration. Could you explain it, this statement? Thank you.
Dr. Lisna, please answer the question.
On behalf
Or,
of Ms. Lisna, I will
okay, thank you, Dr.
answer
Adi,
the question,
please.
but
Yes.
yeah, but sorry, Mr. Beneta, maybe I cannot answer your question because in this work, my part related with activated carbon production. So maybe, I'm sorry, I cannot answer your question.
It's okay, Mr.
Well, I have a follow-up question then, Dr. Adi. So from your result, what is the best application for the activated carbon that they produce? What product can you apply, for example, for this result?
Okay, thank you, Ms. Dini. So actually, in this research we use three kind of activated carbon. So the best treatment is activated carbon with nickel impregnation. So actually in general, cemang has oil like contain high carboxylic acid, right, and triglyceride. And 3,4 hydrocracking is expected to produce more valuable product with shorter C chain. So this process allow an e-metal with non-pair electron with hydrogen gas, to initiate the hydrocracking reaction. So the three main component of hydrocracking product are lauric acid, I think about 30%, and then dodecane about 27%, and tetradecanol, right, about 8%. I hope that answer your question, Ms.
Yeah,
Dini.
thank you very much. It's answered my question. Thank you. I guess because of the time limitation, it's already 4 o'clock. We actually a bit run late than the schedule. So let's give a round of applause for everyone in this the third session. Also for everybody who today has present their talk with a good job and also quite interactive. So I really appreciate today. And before I close this session, I would like to thank Bernadetta for co-chairing this session, and then Dr. Vicky for operating. Also, there's other committee like Dr. Deni Purnomo, Dr. Nisa, and Dr. Yeyen, and Dr. Dian, who actually help us to run this program smoothly. So see you tomorrow at what time, Dr. Vicky? Tomorrow, I guess.
8 in the morning.
Yeah, we will
8
have
in the morning.
We'll have another keynote speaker. Correct?
Keynote speaker. Yeah, keynote speaker from David Christian and Prof. Mirta Karina.
Yeah, tomorrow I will not sharing this session for the. I'll see you again in another next event. Thank you very much.
Thank you very much, Dr. Dini.
Dr. Dini, thank you.
Thank
Dr.
you.
Vicky and
You're most welcome, everybody. Thank you.
Bernadetta, right?
Thank you, Dr. Adi.
Thank you.
Leave the room, and then we can just close it, isn't it? No need to go back to the main room.
Yes, yes. No need to go to the main room. All the participants can leave the meeting. Thank you. Thank you.
I leave this room. Thank you all.
Thank you very much for all participants. Thank you very much. See you tomorrow.